Yes, Venkat.
Yes, sir. Good morning. Good morning for you. Yes.
Good afternoon. Good afternoon.
Yes. I hope yesterday you have practiced that SLD which I have shared yesterday evening.
I did not practice, but I read it and I understood the
Okay.
the symbol from the keys. The reason I could not practice because it was Friday and I was just like too many things to
Okay.
do.
Okay.
And then
Okay.
and
Fine.
then
Fine.
over the
Then,
night I was watching the recording stuff again. The one what we have done yesterday.
yesterday.
That was something like I done, but like what Selva explained there, like about various type of studies. So that's what I was just trying to recapture again. And apart from that, where you were showing the plots, there was a different XO marker and things like that. That's what I was trying to like repractice and recapture again. So that's what I've done yesterday.
Okay, okay, good. Yes, that's a good initiative. Yes, then I will go through the SLD. What you have understand, you can tell me. Then we will go for the source modeling where we have
Yes.
left yesterday, and then Gokul will take the source modeling, and I will
Okay.
explain some important terms which will be used in the source modeling.
Yes.
And after that, yes, as I said, Google will take care of the source modeling, and with that we will wind up the session today. Yes, this is the overall session which we have planned today. Okay.
Okay. No problem.
Yes. I will share my screen.
Yeah, please.
Yes. I hope my screen is visible.
Yes, I can see it. Yes.
What was your understanding from this SLD for you?
The understanding why was in two parts. So they are like two
Oh,
feeder, and
oh,
one is the future, and one is this one where your arrow is. And
yes,
other than that, it is connected to a GIS substation. Is that right? There was another page on this as well. There was a
yes.
GIS
This is the
as well.
GA substation. Yes.
Yeah,
You are
yeah,
correct.
GIS. Yeah. So from the top, if I go, so there's a surge arrestor right
Yes,
there,
sir.
and then this is a, a voltage transformer. Is that right?
Yes, yes, VT,
And then
yes,
on the
hold.
another side is a earth switch. On the another side,
Yes.
yeah. Then another switch. It's called something again in different way. And then the circuit breaker.
Okay,
And then
I
again,
hope this is not yet switch. I hope
which
it
one?
is an disconnect. Uh, it is
No,
a
they are all
motorized.
MR like yeah, they are
Yes,
yeah, that's
yeah,
the motorized and something else as well. The circuit
yes.
breaker and then again a motorized a earth switch and then it comes to the bus.
Bus, yes.
Yeah.
What type of bus bar arrangement is that? Do you have any
No,
idea?
no, I have no idea on that because I don't know the
Oh,
power system study, so I have no idea.
okay. Then we will plan a session on bus bar arrangement. What are the different types of bus bar arrangement which are all available? That session we can plan tomorrow, right? We
Okay.
will explain what type of bus bar arrangements are there in a power system. That we will explain because that will be useful when doing insulation coordination projects and all. That we
Yeah.
will, and will also helps you in different types of bus bar arrangement which are all available in the real time. Okay, that
Yes.
we will do.
Okay.
Yes. Then, uh,
Yeah, and then after that, roughly the same scheme until to another level, and
late.
then
Okay.
yeah, and then it goes to a GIB, and then after that to a transformer, 400 kV.
Yes. Yeah.
Yeah, and then goes to the distribution feeder.
Distribution feeder. Yes. I hope
Yes.
you have gone through the SLD. And do you have any idea about how to model these equipments like that? Do you have any idea about that?
And well, I modeled the circuit breaker before, but
Okay.
I I modeled a bus as well, just like two bus connected via a line, a pi
Line. Okay.
circuit. But I never modeled like earth switch or voltage transformer or current transformer or earth switch or the isolator or anything like that. I never modeled, and to
Okay.
be honest, I have no clue. Like I know how to model it, like each
Uh,
component, but I have no clue like how do you start. For example, if you got
okay.
this SLD, like where to
Yes.
make start.
Okay. Then I will go through that. First of all, what we have to do is like The first part which comes to our mind is like we have to first get the data from the customer. What are all the data we will get from the customer? That data we have to get from the customer. Okay.
Yes.
That part we will just wait a minute. Just wait a minute. I will show you. I hope my Excel sheet is visible to you, right?
Yes, I can see it. Yes.
Yes, yes. Like this, what are all the datas we need from the customer? That data we have to get from the customer. Okay, because that are all the inputs which has to be given by, that has to be given by the customer to take the studies further. Okay, like this we have to form
Yes.
on Excel sheet, or else the model which will be followed in your organization, like that the whatever the way we have to ask like the data which are all the requirements from our side to the customer, and we have to send it to them, and we have to get the data from the customer. Here you can see this, we have asked for transmission tower data, switchgear data, transformer data, surge arrestor data, like that cable fault level, that the data and all we have to collect from the customer. In this Excel sheet, you can see all the data which we have asked to the customer. Okay, but what we will do is like we will go through a single part. Now today we will take the source part, and we will go through completely through the source modeling, and we let us see what are all the inputs which we have to get from the customer for the particular source modeling. Okay. And
Yes.
before that, I will tell you how the modeling should be performed, how detailing should be the model to be performed for each and every studies. Okay, I will give you some basic idea for that, and then we will go through the uh, go towards our part, that is the source modeling today.
Yes.
Okay, I will just open a file. Yes. Okay. We will start from the source. Okay, we will start from the source. Source can be modeled, as I said yesterday, the source can be modeled like this, in the same manner which I have shown yesterday. Okay, and then this data is particularly specific to modeling of circuit for two studies like TOV. Yesterday we have said like there is something called as temporary over voltage, and there is something other one called as SFO, slow front over voltage, right?
Yes.
For that purpose, and for other studies like ferroresonance, and for that we can for these three types of studies we can use this modeling. Okay, here you can see this, we have modeled the source, and we have modeled the cable detail. Here you can see this, if you go inside, we have modeled the cable detailed
Yes.
manner, and then after that we haven't modeled that much detail about the circuit breaker. Here we have taken the general circuit breaker, and we have kept the same model of circuit breaker to model the circuit breaker, right? Why I'm saying is that when we go to other studies, you can feel the difference. Okay, I will get you through the model, what I have done. Okay, and that is which is inside this module, this particular module, which is called as RAF super substation. Okay, this is how we have modeled it here. And then if you go inside this Salaya super substation, what it does is like here we have also a source which is an incomer feeder to the particular substation called Albara Super 1 substation, which is under our scope. Okay, so we have got information for the particular above feeder and this feeder. But what we have to do is like we have to get data for the above two buses. We have stopped at Salia Super, but what we have to do is like we have to get data for the above for two levels. We have to get the data. I hope you can understand what I am
Yes,
saying. The
I
two
get
levels.
that. Yes.
For two levels, we have to get the data from the customer. Okay,
See,
in
but
this,
that wire you drawn between. If you go one step back, please, on your block diagram.
yes.
So you connected
Uh,
the RAF super just via one wire. Why
uh,
is that?
this wire you are asking, right?
No, the middle wire.
This middle wire is nothing but here I have to connect it like this. This is an incomer from here.
Yeah,
I hope now you can understand.
yeah. And what these three wire are then that you drawn
These
there.
three wires are all like these are all the cable feeders, which are all incoming from the particular substation.
And what about those two? The one you two drawn there. What those two are?
This is also and one of the incomer for this particular substation, which is called
Oh,
Albara Super 1 substation.
okay.
Okay. In this example, we have seen there is only one incomer for this particular substation,
Yeah,
right?
yeah, yeah.
Like this, what we have done is like here
And
we
this
have
SLD is for Salia Super. Is that right? The one.
yes, the SLD which I have shown here, this one you
Yeah.
are asking, right?
Yes. Yes.
This one is for another project. This one is
Okay.
for another project. But what I'm trying to explain is that how detailed we used to model the equipments. That is what I'm trying to explain.
Okay.
Okay. In this particular substation, what we have is like we have five incomers from the other substation, like RAF Super and Salia Super substation. And for this Albara substation, as I said, this is our scope. This substation is our scope. So whatever the situation which happens, what happens in our system, that is what we have to analyze. Okay. Here we have from RAF Super, we only have three cable feeders. I hope up to this point you are clear, right?
Yes. There. That's clear. Yes.
Okay. And then from Salia Super, what we have is like we have transmission tower from them. Okay, that is a cable, but here we have transmission line.
Transmission line
Okay,
tower.
here
Yeah,
you
I can see that.
yes, yes,
Yes.
yes. Here you can see that here also we have modeled the source, and this is the tower modeling. Okay, this is the tower modeling for SFO and TOV studies. I hope that is clear up to
Yeah,
this
that's
point.
clear. Yes.
Yes, we have modeled the transmission line. That is also we have that one also we have modeled detailed. Here you can see this. We have given the configuration for the particular tower, the data which we have collected from the customer. For that we have modeled the tower, and then we have to match some of the what do you say that there will be something called as resistance, inductance, like that and all that properties we have to match in the uh, match for the particular model, and then we have to proceed to the studies. Okay, that part we will see in the upcoming days. Okay, now we are going into our substation, which is our scope, the 400 kV substation. Here you can see this, we have modeled the 1.5 breaker scheme, right? Here
Yes.
here you have
This is a
seen
GIS
yesterday
diagram,
we
right?
yes, this is also a GIS which has an 1.5 breaker scheme. Okay, so this is since it is an SFO and TOV model, we don't need to model it as an that much detailing. So we have modeled with some breaker, which are all the breakers which are available that we have used and modeled it. Okay, this much detailed modeling is enough for what we say that for TOV and SFO models. Transformers we can generally model like this, and reactors also we can generally model like this. Okay, these are all the equipments which are all available in the particular substation. Okay.
Yeah, that's all right. One thing is how did you calculate it the Z for the source impedance? Some kind of impedance. If you go to the one of the
Yes,
just
yes. That
for
part, that part we will come. That part we will come. In the second
yeah.
half,
So
we are
later on you will show me how to develop this step
yes,
by
yes,
step. Is
yes.
that
How
right?
to match, how
Okay.
to get those X and R values, how to calculate that we will see. Okay.
Okay. Thank you.
Yes. This is how we have done the modeling for SFO and TOV. But when we go for the other studies, like what are the other studies which are all remaining? Fast front over voltage, which we say it as lightning studies, lightning over voltage studies, right? Lightning over voltage studies, and then
Yes.
other studies is called very fast front over voltage studies, VFFO. Like yesterday, sir has said, like no, very fast front over voltage, and TRV studies, other studies which are all remaining, right?
Yes.
Yes. For VFFO and TRV and FFO, for that we can use the same model which I am showing here. For cable modeling and transmission line modeling, we can keep the same model which we have um, used for the VFFO and FFO studies. Okay, and the difference is like here you can see this. Um, this is an 1.5 breaker scheme arrangement. This is an 1.5 breaker scheme arrangement which you have seen before now inside the particular substation. This is an 1 breaker scheme. This is an 1.5
Yes.
breaker scheme. Right? Okay, here you can see this. This is an GIB. This is an GIB, which is an incomer, for the particular substation. We can just, I will show you how we have modeled detailed. Here you can see this. We have model detergent,
Yeah.
with
Capacitor.
the only capacitor. Okay, because this is for TRV studies. But if we go for But if we go for VFO studies, here you can see this. Here we have modeled differently, right?
Yeah, line as well.
We have used the transmission line model to model this. What we say it as? We say it as an surge impedance modeling. Okay, here we have used
Yes.
the surge impedance modeling. Okay,
Yeah.
that part we will come later when we go through different types of studies. Okay, and then this is the main difference between how we model a substation in for VFFO and FFO studies, and for the TOV and SFO studies. Here you can see this. We have modeled all those things detailedly. Like we have modeled the capacitor. Here we have modeled the surge impedance. Mostly here you can see this is an circuit breaker. This one, like here there is something called as something shown as blue color na. If we go inside this is an circuit breaker model. Before that, what we have generally used this only circuit breaker, and we have modeled this. But here, since we have to model somewhat more detailedly, here we have included all those surge impedance and capacitor to model this.
Yeah.
I hope you can feel the difference between the modeling. Yes. Okay, this part we will come later. I'm just showing you overall view how to model the equipments for different studies. Okay.
Yes. You basically creating like a block diagram and then embedding information inside them. Is that right?
Yes, yes. I hope you have also tried this block diagram using this component wizard.
Yeah, yeah. I only tried one for yeah, capacitive
Uh,
compensation just to see that.
okay,
But I
okay.
I am I am not that much expert like you showing on the screen.
Okay, okay. That we will come because as I said, we are going through equipment by equipment. Then we will show you how to model this. Okay.
Yeah, if I learn something like this, what you're showing in my screen, so that would be
You
very
can do
nice
also
to
amazing
start
stuff.
my
Yes.
career. Yeah.
Here you can see this that the main difference which I want to show you is like today since we are going for the source modeling. Here you can see this. Here we have modeled the source detailed, like we have modeled with the H by R ratio which we have got from the customer, like that we have modeled. But when we go for this VFO4, this source modeling doesn't have much impact. We might have used to the uh, just a just a simple ideal source model which we have
How do
used.
you know the? How do you know like which type of study have an impact of source model and which don't, just based on the experience you do or is written somewhere?
Okay, okay. That is what because what we usually do is like this SFO and VFFO, sorry, SFO and TOV. What it does is like he this. this study which impacts our substation depending on the outside parameters also, like the transmission line model, cable modeling, like that. Okay.
Yeah, and VFTO only matters what is in the
VFTO
GIS.
only matters only within the GIS due
Yes.
to the action, due to the
Yeah,
switching
I
action which
understand
is
that much.
performed,
Yeah. Yeah.
which is performed inside the GIS, so that there is no need to model the complete modeling which is away from the GIS. Just we have to insert some source, and we have to apply some what do you say, that some 1 per unit of voltage, and we have to perform that study. That part we will come later. Okay. Just I'm just
Yes.
showing how
Yes.
a source is model. Okay.
Yes.
Okay.
And
Yes.
Venkat,
Done.
do you also carried out or have done any line coordination studies? Like for example, you model a transmission line tower, couple of spans either side, and see if tower footing is 10 ohm. Say carry out like a lightning strike and see if there will be
Yes,
backflash.
yes. I will show you. I will show you. I will show you. We were asking about FO4 studies, right? Fast to front. That is lightning over voltage studies. Yes, I will show
Yeah,
you.
I that's like one of the main aim that I want to do as part of my earthing works.
Yes, yes.
Yeah, so that is
I
really
will show you.
important for me. That I would like to understand.
Yes, I will show you.
You don't need to show me now. I mean, whenever you have a that in your schedule, you can show me that day. I was just asking.
Yes, yes. Just I'm just I will show you how we have modeled that also. That is not a issue. Here, can you see? Can you see this?
Yeah,
Here we have modeled
yes,
the tower.
yes,
Here we have modeled the tower, and with the tower we have done. This is the inside. What we say that this is an outer view. Like you have said, no, the component wizard. You see
yeah,
that
yeah,
component wizard. We have modeled this outside view to show for the customers, and after that, when we go inside this tower, we have modeled the tower detailed. Like
yes,
this is a ground wire, and these are all the phase conductors which are all there in the
yeah,
there are which are all there in the tower. Okay, and
yes.
then we have put some tower impedance, right? Now you have said like 10
Very good.
ohm or
Yes,
5
yeah,
ohm, like that you have said, right? This
yes.
is an tower impedance. Okay, with that we used to perform some two to three cases with 5 ohm, with 10 ohm, or with 15 ohm. 5 to 10 is the normal cases which the customer asks from us.
And what happens if there is a risk of flashover? Then what you will do? What's the mitigation for this case, for example, on the
Happens
overhead
is
line?
like for mitigation what we used to do is like whenever the lightning flash occurs, when it will travel towards the substation, right? It will
Yes,
take both the path,
tower
like it
ground
will
and
travel
substation.
towards the substation as well as the away from the substation, right? What
Yes,
are all the what are all the what do you say that what was the wave which is traveling towards the substation? It
yeah,
will damage our substation, right? Yeah,
yes,
because there will be lot of equipments in our substation. There will be a particular insulation level for the particular substation, right? I hope
yeah,
you
yeah,
know
yeah,
about what is insulation level. Yes, yes.
yeah.
There will be a particular insulation level for the substation. What we used to do is like we will check what is the impact which is created due to this wave, how much voltage it has been increased by the particular lightning, and we will compare it with the particular insulation level of the substation. Okay. Let
Right.
us say due
But
to this lightning.
you don't do that. Just say, for example, your subject is tower, right? And you want to
Uh,
understand like if the tower is hit by lightning, no substation. I mean, of course, you will model it, but if you are talking
yes.
like a tower in middle of say 60 kilometer long line, right? And you're just talking a
Okay.
tower somewhere in like say maybe 30 kilometer in the middle, left, right. So if that
Okay.
tower is like going to be hit by lightning and your study shows that there is a risk of backflash over along the insulation string, what do you do like
Okay.
other than reducing tower footing? You will put like surge arrestor on the tower.
Yes. There is something called a surge arrestor to the tower also we can put, but only I hope you have seen some. some cases like there will be a surge arrestor in the tower also to reduce this impact due to what happens is like when there is an breakage, what happens is like your power will be shut down, right? So to
Yeah.
avoid that, what they will do is like they will use some different components are there, right? For transferring the surges to different towers and making it ground towards to turn it over to the ground, so that your ground your tower won't be getting affected, like that studies you are asking, right? Am I correct?
Yeah, 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 yeah. That's right.
Yes, for that
Understanding.
also
Yeah,
we
please carry on. Yes.
yes, yes. That is what you are asking, as I understand. Okay, but
Yes.
here what we have did is like you are asking for the particular continuous length of 60 kilometers where your lightning has a strike in a particular location, which is much more away from the substation.
Yes.
There
Yeah. I
what
was asking
happens
for
is
tower interest.
uh,
Yeah. What do you do with tower?
tower.
Yeah. Yeah. I know you're trying to
What
show the surge arrestor
uh,
placement. Yes.
surge arrestor placement. That is what we will usually do. Okay,
Right. Right.
but here what we have done is like we have artificially created a lightning current because this tower is much more closer to the substation. Here with
Yeah.
this substation,
Yeah.
this tower will be much closer to the substation, and when the lightning hits on the particular tower which is near to the substation, and what happens, what impact this lightning current will create inside my substation, that is what we are going to analyze in fast front over voltage studies. Okay.
Yes.
If you have found that your the lightning which has been happened in the site is going to damage some of your equipments. Let us say my insulation level of the equipments which is inside my substation is like 1500 kV, 1425 kV. Then the voltage which has been increased due to this lightning has been above this level. Let us say for 1125 125 level. What we have to do is like we have to go for surge arrestor placement. Here you can see this is an one surge arrestor. Okay, this is an surge arrestor, which is with
Yeah.
this surge arrestor has been placed in the entrance of the substation. Okay, like this, what we have to do is like we have to suggest some surge arresters which will be required to reduce this effect. Okay, so that your substation equipments will be protected. That is what uh, the main objective of this FO4 studies. I hope up to this point you are clear.
Yes.
Yes,
I am clear. Yes.
thank you. And then that is what the modeling which we used to perform for VFFO. You have said like I don't know how to model a earth switch and all. For earth switch arrangement and all, you don't need to model for the before for the studies which I have said earlier, like TOV and SFO. There is no need for modeling the earth switch and all. But when we come for this VFFO FFO studies, we have to model the earth switch. Here you can see that this is one earth switch. Can you see
Yeah, I
this?
can see that.
This
Yes.
this edge switch we have modeled it as and surge impedance, right? For TRV studies we might have modeled it as a differently. Here you can see this when we go inside this earth switch. Here you can see this we have modeled it as a capacitance. Like this, we used to change the model depending upon the studies. That all depends on the how much frequency your studies is going to happen. Okay, that much detailed modeling will be required when your frequency is higher. Then we have to go for this much detailed modeling. But when your frequency is somewhat lesser, then we can go for this like TOV kind of modeling, and this TRV kind of modeling also can be used when the frequency is in between these ranges. Then we have to go for this capacitance kind of modeling. This is a overall view about how to model. Depending on the how much frequencies the studies will be done, that we will come in the later. Okay.
Yes.
Yes. Okay. Uh, ca- can you just tell me what you have understood from what I have said like this. Can you summarize it just a bit, how
Yeah,
what
you
you
show
have?
me like if you are going to do like a TRV studies and switching study or a VFTO study and a lightning one.
Uh,
So how we
yes,
can model the different components. So if the idea is basically create like a, a component and then put the more
uh,
component inside and try to
try to
correlate
model.
them so then they the control system work with each other. That's
Yes,
what I
yes.
understood. And depending
Oh,
on the TRV, there is a requirement of like for TRV and switching, you can model a simplistic source. However,
no.
uh,
Oh,
oh sorry, detailed source. Yeah, and when it comes to VFTO, then you need to model like GIS in a particular
detailed manner.
detailed way.
Yes,
Yeah, yeah.
yes, yes. Yes, that is what we have understood, and then we will start up from the source. Okay, today we will start up from the source. In the upcoming session, we are going to model a transmission line, and after that we are going to model some cables, and then after that what we
Yes,
are going to model is like we will go to the load modeling. With that four types of after that we will see the transformer modeling, and if there is any reactor, how we can model that. Up to that we will see, and then at that point what we will do is like that are all the important things which will be which are all need for performing TOV and SFO studies. With that we will see some case studies from there after completing the reactor modeling. With that we will see some case studies for TOV and SFO, and after that we will go for the detailed modeling. After that we will go for VFFO, FFO modeling. Okay. In this between,
yes.
we will do some basic works on the other softwares too. Okay, to
Okay,
make you
great.
understand the overall view, overall to give you overall view
Yeah,
of the
I don't use other software, but like for my like in India
for
when you do the
conceptual
yeah
for
when you do
concepts of
yeah when you do the earthing study, you generally
uh,
get told like this is a 63 kiloampere and 40 kiloampere, the rated current of like circuit breaker to do the design.
circuit breaker.
But
Yes,
what happens here is the customer gives us the infeed from various substation using PSSE and Dick Silent.
yes.
And I never use the software itself, but I can, if I have the single line diagram, I can say okay, this is my central station and say this is faulted, and then it is connected to by like
Two.
another 3 4 substations, so I can read the fault in feed node number and PSSC printout. But I myself never done it or
Uh,
never even open up another software like
Open up.
PSCAD or this ETAP. Sorry.
Please. Okay, okay, okay. I understand. Yes. Okay, then we will go to our subject today. Then today we have planned for something source modeling, right?
Yes, please.
Yesterday we have some basic about the source modeling, right? Today we will see what are all the source modeling we will be using for our particular studies. I will just copy this one and I will paste it here. Okay, this is nothing but an ideal source. Okay, this is nothing but an ideal source which we have used for VFTO studies. Now here you can see this, we have used this type of modeling for VFTO, right? What we can do
Yes.
is like I will tell you some basic things which we have to do for modeling an ideal source, because this is an easy one. Okay, so what we have to do is like we have to go inside, just double click it. If you want a three-phase view, you can keep it as a three-phase view. If you want a single line view, you can keep it as a single line view. But if you want to make this single line view into a three-phase view, there is something called as a sequencer. I hope you know about this. Have you came across this option?
Yes, I have seen that. Yes.
This sequencer, right? Which will be used to convert the single phase into three phase. If we put here, then what we can do is like we can connect it to a wire, and we can say here we can take it as a single phase. Okay,
Yes. Yeah.
I you have
I
done this.
understand that
Okay,
much. Yes. Yeah. I
yes,
done this. Yes.
okay, and then we will go inside this source. Here you can see this, as I said here, yesterday, here you can give the name for the source. Since it is an ideal source which we are going to take, I have kept my ideal r equal to 0. You have other
Yeah.
options too,
Yes.
since we are going to take it as an ideal source, I am just going to take my r as equal to 0. Okay, and I have taken my star point as grounded. If your system is not grounded, you can keep it as no. If your system is grounded, you have to keep it as yes. And then, as I said,
It
this
is
is
mostly
for
grounded, isn't it?
yes, yes, it is mostly grounded. There won't be
Yeah.
any ungrounded systems and all. Okay, it will
Yes.
be mostly grounded. Yes. And then what will happen is like we will go inside the signal parameters. Signal parameters. There is an option called as behind the source impedance, and there is an option called as at the terminal, right?
Yes.
There is something
Yes.
called as at the terminal, and what happens if I choose behind the source impedance, and what happens at the terminal? Let us see. Okay, here I have chosen behind the source impedance. Okay, now what we
Yes.
can do is like here you can use external control for voltage and frequency. What happens if I chose yes? Here you can see this, there is no external control for this. But when we
Yes.
use yes and yes, and when we click OK, here you can see this, there is some option available to
Yeah.
give
To
the data
control voltage
externally.
frequency.
Uh,
Yes.
yes, yes. What we can do is like we can use this integer constant, right? There is something called as integer constant or real constant. Here you can use this or use this.
What
Okay.
is the difference
Uh,
between the integer constant and the real constant?
Yes, in integer constant, what we cannot do is like we cannot give some 1.5 values and all. Can you understand?
Ah,
This
right. Yes. Yes.
decimal values and all
It
we
should
cannot
be. It
give
should be
in.
pure unit number. Yeah, I get that now.
Yes, unit number. And if you are going for real constant, we can give
You
some
can give the fractional number as well.
decimal values and all like that you can give. Okay.
Lovely. Yeah.
Yes, yes,
Understand.
yes. This is. Then what we can do is like here we can give the external control like as I did here. Here I have used the external control, but I have inside what I have done is like I have kept the voltage as 220, but in using the external control I have kept my voltage as 220, 231.
Why did you
Okay,
put
like
that 230 instead?
what we do is this is generally to perform short circuit studies. What the customer will do is like they will give you some data. Just wait a minute, I will show you. Here, can you see this? Here they have
Yes,
given
I
the
can see.
value to
Yes.
one. Yes, here you can see this. Wait a minute, wait a minute. I will just take a pencil. Here, can you see? Here they have given it as an 1.05 per unit, right?
Per unit. Yes.
Per unit. Whatever the what this symbolizes, what this says is like whenever they perform short circuit studies, what they will used to do is like whenever they perform short circuit studies with IEC standard, what they will used to do is like they used to take some C factor. Have you heard about this term C factor?
No.
Oh, okay. That part we will take. That part we will take in the upcoming sessions. What is C factor and what causes the what effect this C factor causes in the calculation? Like that we will tell you. Okay, but to understand this point in an easy way, what is it? I will tell you. What to this what this C factor considers is like I don't go for the C factor. What this per unit says is like here it assumes a condition like when my voltage is higher than the higher possibility value, like that it assumes. Okay, when the voltage is higher, what it does is like it will provide some worst case fault current. Hello.
Yes. Yes.
Uh, when the voltage is higher, it will give you higher fault current. That is the worst case, which all the power system engineers will consider, and they will perform the studies. Okay, this is one way to calculate the fault current for the worst case scenario. So that
Okay.
to make this happen, what I have did is like I have taken a 5% margin for the particular 220 kV. If we take a 5% margin, increase, just increase the 220 kV to 1.05 per unit. What happens
Yeah,
is like
yeah,
I will
yeah.
to
It will come
231.
to
That
231. Yeah.
231. That is what I have done here. To make that scenario happen, I have kept it as 231. Okay.
Yes.
Okay. Yes, that is why we used to give some external control options that from that we can give some external options.
Yeah.
Okay,
In
that is
this case,
the
the 220 kb doesn't matter. Whatever you write inside that, right?
whatever right inside that. But with the external control, I can give any voltages. That with
Yes.
that we can control the voltage here. Okay.
Yes. Yes.
Yes, that is the main difference. And after that, where we have left here, like behind the source impedance, and we have shown you how to use this external control. Now we will kept it as no. Before that, if I kept it as yes, here you can see this option automatically disables. Can you see this?
Yes.
There is something 230 kV is there, but when I keep a external source, external control voltage as no,
No. Then.
sorry, as yes, it will be disabled. If I kept it as no, then this option will be enabled.
Yeah.
The here itself you can give the voltage.
Yes.
Okay, like this, or this option varies, and this ramp up time yesterday I have
And
shown you,
that
right?
voltage is like your line to line RMS, like which is already your line voltage. For example, is 220
Line
kV and
voltage 220 kV.
132
Yes,
kV, or yeah.
yes, yes, yes. Here itself it has mentioned like AC
So
line to line
yeah.
RMS.
So it is
Okay.
always that, right? You don't need to change it to another value. For
Uh,
example, you don't need to put like 132 kV divided by root 3,
root 3 and all.
76.
No, no, no. It is
Okay.
not required. Here you can
Whatever is the rated voltage of the system, you can just put that.
system. You can just put that here.
Okay,
Yes,
great.
yes. And here I hope this point I have explained to you yesterday, right?
Yeah, I
About zero
explained. Yeah,
zero.
you
Uh,
explained that the time is to ramp up to the yeah
ramp up the
voltage.
time. Okay,
Yes.
okay. This phase shift, what it is does is like if you have any phase shift in the supply, generally we don't go for any phase shift and all, because whenever we assume a source, we assume it as an grid. Okay,
Yeah,
whenever
one
we
kV
perform
to
the
supply.
whenever we perform the simulation, what we used to do, we used to take is like we used to take it as a zero, phase degree as zero. It is something called as 1 bar 0, like we used to say like it as flat start mode. Okay, what we used to do is like 1 angle 0 degree. Here
Yes.
what we can see, say it as 230 uh, 230 kV with 0 degree. That is what this symbolizes. Okay, and then the other condition is like terminal conditions. When can we use this terminal option is like when you keep this option to at the terminal, what it does is like it always maintains the whatever the voltage which we have say here, it does always maintains at the particular bus. Here you can see this, there is something here there is a bus, right?
Yes.
Here there is a bus, but if I have chosen, if I have chose the option as at the terminal option, what it does is like it will maintain the same terminal voltage. If I keep it as 1.1 per unit, what it does is like it will take 1.1 per unit of voltage, and it will try to maintain the same voltage in the particular bus. I hope you
Yeah.
understand that
So
point.
yeah, yeah. So whatever you put in the source, you will same receive on the another side, right?
Same receive on the particular terminal which is connected to the particular bus.
And when you do that ever in study or you don't do it?
We don't usually do this. We used to do go for this option.
Yeah.
We will
Signal
keep this
parameter or
behind the
external
source,
control.
and external control of voltage, external control of frequency. With this itself, we used to perform the studies.
Right.
Okay, and we don't need to see this resistance since it is an ideal source. We don't need to see this and all. But there
Yes.
isn't something called as monitoring, right? Monitoring.
Yeah.
What it does is like here when we I hope yesterday I have explained this point. What we have to do.
Yeah.
This
Whatever we want to watch in the output, we can specify here like
we have to specify
ID,
here,
ID,
and we
IC,
have to
voltage,
yes,
and it,
we have to use the same name outside to get
to make sure that
to
the
visualize
control
the
works. Okay.
out.
Yes.
Yes, yes, yes. I hope you got it.
Yeah. Yeah. I
Yes,
got it. Yes.
the, yes. The, that's that's it about the ideal source. Then I will move to the source which we used to take for the insulation coordination studies. Okay, there are other sources also. Here you can see this. There are a lot more sources also available, but the option which we used to take, like we used to use some ideal source model, and we used to use this model. Okay. Other sources, there is not necessary to use this. We usually used to perform the simulation with this model. And other than that, what we used to do is like we used to use this option, this current source, where we use is like here. Just click on it. Here you can see this
Yeah.
for the here you
Yes.
can see for lighting purpose to produce the current.
Yeah.
We use this current source model. Like this,
Yeah.
these are all the main components which we will be using for the insulation coordination studies. Uh, yes, with this I will go to this source. Here, this is the source modeling which we have been going to see. Here, as I said, we used to give the name for the source and what is the base MVA for the particular network,
You choose the
and
100 MBA always, or is something depend on
uh,
the study?
how to choose this base MVA, that is being explained in some standard. How to choose this base MVA?
Okay.
Please give me. Can you give me a minute? I will show that too. Just wait for a minute.
Yes. Sorry, I done my power system like 2011. After that, I all done is something different, so I forget if it's
No, it
base.
is not an issue. It is not an issue. I will show you. Not an issue. What are all the doubts you have? You can throw it on us. But if you know, we will surely answer your question. If you don't know, I will say like I will get you back. That is what I.
Yes, that's great. Now you're doing really well. You explaining in a nice way. That's how I want to learn the things,
Oh,
like know
oh,
like each and every single item, what it is
uh,
and what it does and what it don't does. Because end of the day, every study is different. So when you do one, then if you know the details, then you can build things on your own.
yes, yes, yes. That is what. That is the way we have to teach to others also. That is the way we have to learn ourselves also.
Yeah, that's
Yes.
that's
That.
what I do in my study. As long as
Yes.
I know some basic and how to build like one or two model, then you can twist and you can change the parameter and you can
Change the
learn on your
parameters.
own.
Yes, yes. Here you can see this. This is an snapshot from the standard called as
Yes.
IEEE standard 3002 series. Okay, for load flow. Okay, for load flow, this is the series which we used to take load flow IEEE standard
Yes.
3002.2. Okay, from that I have taken a snap of it. How to choose the base MVA. Here you can see this. In power system studies, the base voltage is usually selected as the nominal
Yes.
system voltage at one point of the system. Okay, such as the voltage rating of the generator or the nominal voltage of the delivery point at the utility supply. This is what we have seen up to now. Yes, like line to line voltage we have said no. This is the point
Yes.
they have said that as nominal voltage. Then they have been coming to the base MVA. Here they have said it as base KVA.
KVA.
The base KVA can be similarly taken as the KVA rating, one of the predominant pieces of system equipment, such as generator or the transformer. What they have been, but usual practice is to choose a convenient round number, such as 10,000 for the base KVA. Okay. Then what they have did is select the data selection has some advantage of commonly when selecting studies are made, while the former choice means that at least one significant component will not have to be converted to a new base value. What they will usually say is like the base MVA which we are going to choose. Okay, it should
Yeah,
be
you can choose the one MB of one of your transformer, or you can just assume a value in a group of like 100, 200, 1,000, 500. Is that right?
1,500 like that we can choose. But what just wait a minute. Some things they might have explained in IEEE 3 standard itself. Just wait for a minute. Can we have some 2 minutes break? I will take some water and I will come back. Hello? Hello?
Yes, yes, sure. I will do the same. No problem.
Yes, yes.
Take your time.
I will just come back.
No
Okay,
problem, mate. Take your time.
just 2 minutes.
It's fine.
Yes, yes, yes. Himanshu, can we start?
Yes, yes, please. Yes.
Yes. Yes, this is one of the standard called as IEEE 399. From this standard only, I have took that base KVA. Huh. It is. Can you see this?
Yes, yes.
This is where I have took the snap from that. What they have
Yes.
been saying is like you have to take the base MVA as the rating of one of the generator or the transformer, but
Yeah.
the common practice is like they have to
Yeah. Take a
use a round
multiple of
number
hundreds.
or as
Yeah.
multiple of hundreds as a base KVA.
I get
Okay,
that.
because yes, because what it generally does is like if you choose any rating of the particular transformer or the generator, what we have to do is like we have to convert all those equipments to the
That
particular rating
particular
of the
multiple of that
yes,
particular
yes,
rating. Yes. Yes. I
rating
remember
of
this. I done I done this in my power system. But
okay, okay,
that was like in 2010 or something when I was in like
okay,
third year engineering. So it was long
engineering.
time back. After that, I never done anything like this.
Then okay,
That's why
okay.
I
If you
asked.
want, if you want to, what do you say that if you want to revise back that, you can go through this standard IEEE 399. You can get it from the website
Yes.
IEEE Explore, and then you can go through this. Here they will be explaining what it will be mostly helpful for you to brush up the things
Yes. Yes. Yes.
this calculation has been done because most of the times we will be talking about the per unit quantities and all. But
Yes.
if you go through this standard, you might get a knowledge about how they have been coming with the per unit. Okay.
Exactly. Yes. I will do.
Yes. That's it from how to choose the base MVA. And next part is like as I said, we have to give the nominal base voltage, and then after that we have to give at what frequency we are going to perform the studies, and then these are all the things which we have explained before. This infinite bus we don't be using because what are all the sources which they provide, we will be modeling it as a non-infinite bus only. Here we will take it as no. And then what we used to do is like here you have to choose yes. What it does
Ah,
is
that's the
like there is
important one. Yes. Yeah.
yes, there is something called as zero sequence and positive sequence, right?
Yes.
I hope you don't know you know about that zero sequence and positive sequence components.
Yeah. I know this, but again, the question is, how do you calculate them to put here? What
Okay, okay.
the client give you them?
That part I will show you. Here you can see this fault level, right? This fault level document.
Yes.
You have to take it as an input from the customer itself. Here you can see
Ah,
this.
okay. Yeah. Right.
Here you can see this. There is something called a zero
Yeah.
sequence
Zero
component, right?
sequence per unit. Yeah. X naught per unit
For
speed.
resistance, reactance, and for
Correct.
susceptance, they have given all
Capacitance.
those
Yeah.
parameters.
Yeah.
Yes.
Yeah.
This value we have to collect it from the customer itself.
And if the client don't give you, then it's almost very difficult to calculate. Is that right? Because without
Uh,
having the knowledge of their whole system.
we, you have to ask them to give those values. These are all the main details which we have to collect from the customer.
See the yeah. Another question on this. You were showing me some Excel sheets. How what data you request at the end of the
Yes.
course. Would you be able to give me a copy of that? Of course, by deleting your client name and hiding the
Yes,
just to
I
give
will
an
help
just
you.
to get an idea. You can delete
That
your
is
logo, for example, and client data or whatever, and just
okay.
give me
Okay.
the
That is not
Excel sheet like
that
what
is
is
not
required.
okay, okay, that is not a problem. Whatever the things which we are teaching, what we used to do is like after teaching all those things, we will go to this particular Excel sheet and show you what are the data which we have asked from the customer. Like that, we will show you. Okay,
Yes.
and then you can get this data sheet also if you want. Yes.
Yeah, that would be great. Yeah.
Yes. But what I would prefer is like uh, you should know what are the data which we have to collect from the
Yeah, but
customer.
well, that's what I'm saying is like once I do the course, of course I will know most of it, like
Yes,
what I'm
yes,
going to
yes,
ask. But just as
yes.
a notes, like okay, these are the things I need to ask.
Things which we have to ask from the customer. Yes, I hope after completion of this course, you will get idea about without giving this Excel sheet itself, you will get some idea about what are the inputs which we have to collect from the
Yeah,
customer.
yeah,
Then you
based on the
can
thing you're
re
teaching, definitely. Yeah.
then we can verify with the data which we have collected with this data sheet if when we share this. Okay.
Yes, that's right. Yeah.
Yes. These are all the data which we have to collect from the customer, and then next part is like impedance data format, right? This impedance data format, how you are going to give the data, right?
Yeah,
Mostly we
right.
used to do give the data as R plus JH format, and so because most of the customers don't give this impedance and theta values. The most what is it? The most easy way to give the data is like with using R plus JH format. Okay.
Yes,
Oh. And then this graphic display I have shown, this display details I have shown. Yes, I hope you don't know about this.
yes, yeah, I know that. Yes,
Yes. For positive sequence, we have given some data. How to feed this data that will be dealt by Mr. Gokul, which we have planned to take it today in the next
yeah,
part. Okay, in the coming part. And for zero sequence, how we have to give those values from the values which we have got from the customer, how to convert it and how to give it. This part will be given by Mr. Gokul. Okay,
yes.
and then this I have said you right, and then what was my do you have any idea about this fault current instance? At what instance this fault current happens and what impact does it creates with respect to the fault current magnitude? Do you have any idea about that?
No, I use the fault logic just by entering like what will be the time of fault based on the simulation run like you were showing yesterday, and then I also specify like how long the fault should be,
Ah, okay,
and
okay.
then of
Yes,
course
I have
using the
shown.
graph I can see. Yeah,
I have shown you like yesterday, right?
yeah, yeah, yeah.
Yes. In
And
this,
I
I will
also done
show.
somewhat similar myself. Yes.
Okay, okay. Then now I will explain you about what impact this H by R and the uh, what impact this H by R and the instant at which the fault happens. That I will explain now.
Okay,
Uh,
please.
uh, yes, I will explain you, and then you will get some good
And see,
idea
another
about.
thing is maybe a silly question again. See the bus number you shown on the blue, right? That bus. So
Uh, yes,
that that bus we specify just as a bus, right? Is
yes,
just
yes.
basically, yeah. It's
It
just
is a
basically,
basic.
yeah.
It is a
But it's
basic
just
thing.
a
I have.
node, right? It's nothing else. It has no electrical significance. Is that right?
Yes, yes, it is just a node where we can take multiple outputs from this particular bus bar. Yes.
Yeah. So
Uh,
that's just an electrical point. If I just like create a bus and that's it. I
yes,
don't
yes,
need to worry about any other data about bus,
yes.
right?
Here it is bus, right?
Yeah, yeah, yeah.
Just pick it. You can give a name for the bus and you can give voltage as 400 kV at whatever the voltage you want, you can give it inside. That's it
Okay.
for
Yes.
the bus. Yes. Yes. And then I will show you. Here I'm just going to create a fault here. Okay, I'm just going to create a fault here. Here I have created a fault here. What fault I have created is like I have created a fault called this three phase to ground fault I have created. Okay, and then I have what I have did is like I have put a time logic to this particular fault at what instant the fault is going to happen. Like that I have given the time logic here. And now what I'm going to do is like I'm just going to go with the time just randomly zero 0.3 seconds. Then we will see the graph, what it happens in the graph. Then we will go to the next point. Okay, I have created a fault at 0.3 seconds. My duration of fault is like 5 seconds. Okay. Why I have kept it as 5 seconds is like I'm not interested in clearing my fault, so I have kept
Fault.
it
Yeah.
as 5 seconds. Yes. And I will just run my simulation. Just go to home, and there you can find the
Yes.
run option. To display the fault current, I have used this option. I have used this option to see the current. I have used this multimeter option. When you double click this multimeter, you can see this. I have displayed the instantaneous current and the instantaneous voltage. And then I have enabled this option so that I have to give signal names for the particular input so that I can see
Why you
the
put that as a peak is just a
sorry.
name, or you actually means peak, the
It
it should give
is
the
just
RMS
a
value
name.
itself.
It is
Yeah.
just a name. It's just a name. Here you can keep any name if you want. Here I
Yeah, I
have.
was
I'm just.
thinking like it should give you the RMS value because if your voltage is RMS, is that right?
Yes, yes, yes. Now we here we are measuring only the peak voltage. If you are going to measure the RMS, then you can keep it as name as RMS. That is only for your reference only. Okay.
Okay.
Generally, what PSCAD does is like generally whatever the input which we take from inside, what it does is like here it will be giving the output as only peak value only. Okay. Here it
But my question
here
is the 220 kV itself is a RMS value of the line, right? So the output you will get in a line to line RMS value. Is that right? Or
No,
I'm
no. Here, what is the output which we will getting, which we will be getting is like a
yeah,
single phase ground value.
yeah.
Okay. To understand that, what I will do is like I will keep this time to fault as second because I'm not going to apply this fault. I'm just clicking save and I'm just running. This is, okay. I have deleted the value. Okay.
What version of software the one you're using? It's 4.6 or it's 5?
No, it is 4.5 only. We do have only 4.5 only.
Okay.
Wait for a minute, I will reopen it. I will reopen it.
No worries, no worries. Take your time. How much does software cost in India? PSCAD?
It does cost about uh, 20, 25, 25 I hope. Yes, it is about now the price is like 25 lakhs.
My God.
Yeah, yes. For a single for a single license.
But you can recover that money in consulting business,
Yes, in consulting business, yet that is not an issue. I'm saying because it is
Yeah.
one of the costliest software which is available.
No, but it's still cheaper because the CDEX cost you roughly maybe 70, 80 lakhs, one single license.
CDGS,
Yes, the full CDEX, yes.
full CDGS. Okay, okay.
Yeah.
Yes, we have gone for that also. We have tried that also, CDGS. They have said
Okay.
like about 78 lakhs. They have did. Yes, yes.
You don't need to go that far. If you guys are interested, you can maybe buy like couple of basic module. If you need
Oh,
that idea as well, I can give you a rough idea like what it is and how it works. And if you are in India, you don't need to like go for like very expensive module.
very basic.
There's another software called XGSA Lab. You know that?
I haven't came through that name. I do know about the CDGS, but I don't know about that. Yes.
Yeah, so there's another software called XGSA Lab. So it is
Ah,
very similar to CDEX. I never used it, but
okay.
the manufacturer or the sub publisher of that software like puts so many papers like how it is close to like particular module in the CDEX, and
Ah,
many people use that. I think Nihar Raj used to be a distributor of that in the ABB recently
okay. Okay.
before he left to Adani. So I don't know he still
Okay.
use, but
Okay.
but
Okay.
if you need any kind of help on that part as well, I can show you like
Uh,
what it is. Then you can gauge your requirement rather than going to a sales guy and
uh,
he telling you something else.
yes, yes,
Yeah.
yes. We have experienced that.
Yeah, I mean, yeah, I can tell you like what is your requirement. You tell me like what is your requirement, and I can show you like what module is okay for you, and then you can
Ah,
ask for that price only, rather
okay,
than going
okay,
for
okay.
full CDEX.
Rather than going for the complete version. Yes, yes.
Yeah, yeah.
Yes,
No
yes,
one
yes.
used the complete version anyway in India.
Ah, yes. Thank you, thank you, thank you.
No worries. Yeah,
Yes.
get
Where we have left here. Just we are trying to run the simulation, right? I will try to run the simulation. I hope you don't know about where to take this RMS block and all, right?
I never use the RMS block. I just use the signal
Okay.
and out graph.
Okay. Okay. Now whatever the output which we take from the particular module, what it does is like it will provide only the peak value. Okay,
But
only the peak
why
value.
is that? That's what I was asking. Because see, if you enter the 220 kV there in the source, right? So 220
Oh,
kV is
okay.
your line to line RMS voltage, right?
Yes,
So
yes, yes.
so when you're creating the fault, right? Why it is giving me the peak value, not RMS? That's what my question was.
Okay, okay. Because they have modeled it as like that. That is what the issue with them.
So it's
They
only
have.
for the fault or it's for like anything,
It is for anything. It is for anything. Here you can see
right?
this.
So
There will
you
be.
input the voltage in line to line RMS, and
Ah,
then output you get
yes.
as a peak, right?
Peak, right? Yes, yes.
Okay.
If you want to go for the RMS voltage, then you have to keep click here. Whether you want analog or digital, that format you can keep it here, and you can measure the value for the voltage. But I don't think so. There is something to convert the current to RMS because the blocks which we have used, there is no something
Yeah, I
to
never
see
use
the
that.
RMS.
I
Yes,
never
yes.
use that. But yeah, I understand now. You instead of seeing a peak current value, you want to see that in RMS. That's why
RM,
you put the RMS
then
block there.
RMS block. Where we can find is like here you can go in meters. I hope more on meters. Here you can see this. There is something called as meters, right? More on
Okay.
meters. If you go
Yeah.
inside that, here you can see
That's
find this
RMS.
RMS block.
Yeah, yeah.
Okay. Here
Yeah.
you can find this RMS block. What are the inputs which we have to give is like you have to keep it as digital or analog. And if you keep it as digital, what we have to do is like we have to give the periodizing matter and then the fundamental frequency which we are going to give like 50 hertz or 60 hertz
Yeah.
in which format we are going to. But this is more important when you are taking the value. We have to compulsory change this value or else you will get the wrong value. Okay,
Yeah,
you have to
frequency
keep it
matters a
to
lot, yes.
frequency matters. And the number of samples which we are going to take for the particular cycle, it differs, but we usually maintain with the 64 samples itself. If you want to more accuracy, then you can take it with 132 samples like that and all.
Okay.
Okay, yes, that's it about the RMS block. You have to connect this RMS with the particular signal, and then you have to connect it to the particular output graph. Okay. Now I will try to run the simulation. Here, can you see this?
Yes, I
I
can
will
see that.
show. Yes, I will show you up to 0.0.3. I will click show you. Here you can see this, the value is given for a single phase to ground peak value. I hope
So
you can
that's
see
a
this.
peak value. Yes, yes.
Yes, this is the peak value. How you can match that value? Do you
Then
have
you
any
need to
idea?
multiply that by root 2.
Yes,
Sorry,
231.
divide.
231 divided by root 3 will give you the single phase to a single phase RMS value, and from that you have to multiply it to root 2. You will get 188. Can you get
Say
it?
say that again. Say that again. What you said is 230 is divided by.
231. Yes, 231 is the RMS voltage, line to line RMS voltage, right?
Yes, yeah, and then you
If
divide
you
that to
want a
phase to neutral, right?
yes, if you want a single phase RMS, then we have to divide it by root 3, right?
Yes, that's right.
231 divided by root 3 will give you some value like 133 something.
Yeah,
Okay. And then
and
if
then
you multiply it by peak value,
back,
like
yeah,
root
to
2,
to
root 2
yeah, yeah, to get a RMS again.
RMS again. It is for peak value, not RMS, it is peak.
Sorry, yeah, sorry, apologies.
It
Yeah,
is a
yeah,
peak.
yeah.
Single
For
phase to
RMS you
ground
need to
peak.
divide. For peak you need to multiply. Yeah.
Multiply, yes. Here you can match this value. I hope 188.06 or 9 it will come.
Okay.
Yes. Yes, that is about this voltage and current, and after that,
I was
what I
confused
will.
on this before, to be honest, but you
Ah,
cleared it.
ah,
Okay,
okay,
because I
okay.
was thinking like you get a input as a line to line RMS, so probably
Like,
you get a
oh,
like output in line to line RMS again.
yes. When we started learning, also we have got confused, and we have came to know that there is something called as help will be there for the PS cat. Like
Yeah, yeah, yeah.
here you can see this in the right side corner. Here you can see this. With that, we have came to learn about that and all.
Okay,
Yes.
okay.
Uh,
Unfortunately, in our world, there is a very limited time to learn. There are like projects, and
yes,
you don't.
actually here also the same thing will be going.
But you
But
don't
what
have the
we
timesheet system. We need to put a timesheet. So whatever time a particular XYZ guy gives
ah,
for you, right?
no, no, no.
Say,
Here also
uh-huh,
we have to maintain a time sheet for them.
yeah, and then
Apart
you
from
mean you
that,
need
we
to
have to
maintain
learn.
some.
Yes, apart from that, we have to work later and we have to learn something.
The good thing
It's a,
about you guys is that you already do power system studies, and then you are doing this PSCAT stuff. So it correlate the terms. The problem
okay.
in my part is I was hired as a expert. I'm not expert, but yeah, like that. I was
Ah,
hired as a specialist, and that's the
okay.
biggest drawback in my life, because I wanted to
Okay.
do something else, but the people don't want to. They don't want me to
Okay.
do that,
They
because if they,
want you to
yeah.
move towards the other path. Yes, yes.
Yes, because
Okay.
they don't want
Uh,
it. Because if I do that, so they are in
ah,
problem. Because then who they are going to order, who they are going to say like fix this, fix that.
it,
So
uh,
my colleague also do like side measurement. So in India, the
uh,
side measurement is like little bad. Nobody really does
uh,
that. But here is like when you build a new substation. So before connecting your substation to overhead line, you basically first do
uh,
a resistance measurement, just R value of
okay.
the substation
Ah,
mat.
yes, correct.
Yeah,
Correct.
and
Yes.
then once that is connected to the overhead line wire, earth wire, then it's called
Ah,
a impedance measurement. Then you get R plus JX, so you
ah,
get basically R plus angle. So that's called
angle.
impedance measurement. And then
Ah,
with that,
okay.
we also do the continuity measurement, bonding check, like every plant is bonded or not. And then the fence here is like a separately earth using rods, and it
Ah,
should be kept 2 meter away from the main earthing system or main substation plant to avoid a
ah,
hand-to-hand touch voltage, in two different earthing system. And
yes,
then
yes.
we also do like conditional assessment of previous old substation which was done like 10 year ago, 20 year ago, 30 year ago. So these kind of job we do. And and then or in office like simulation. And then we get like PSSE printout or dig silent printout for like 14 feet. And then we need
Ah,
to
okay.
model like whole lot of system, like from substation going outside, like tower to overhead line, sorry, tower to cable, or cable to tower, or just cable
Ah,
route, anything like that,
okay.
even route up to offshore wind farm. And then calculate
Okay.
ground return current, like
Okay. Okay.
based on the
Okay.
14
Okay.
feet.
Like this, you. Ah, ah, ah,
Yeah.
ah.
And then I also do sometime the pipeline interference studies, electromagnetic field
Yeah.
interference studies for pipeline and telecom. So the people just want me to do that, so I am sick of that. I do it, it's fine. I don't mind doing it, but I also want to learn something else, and then nobody want me to do that.
Okay, okay. But the problem with me is that I have learned all these things in standard only. I have the last time where I have did practical scenario is like in my in my like bachelor's degree. During my college days, I have done some practical things. Other than that, I'm just trying to learn some standards, and I'm just trying to what do you say that I'm just trying to make assumption like this is what they will do things inside like that only. I'm just taking on the things.
Yeah, best thing is like when you speak to client who are doing these stuff, and you send them, and
Uh,
then they give you like a lot of questions and comments back, and then that's what give you like lot of learning. Because when
learning,
I was in
yes, yes.
SES, I was mostly like product focused. There was a lot of
uh,
theoretical knowledge I have, like about soil measurement, impedance resistance, or bonding check, or anything like that. And I never
uh,
had a practical. positions in my role. But when I end up here, so my job
Okay.
is like cover yourself in soil. If you go in
So,
farm field,
okay.
doesn't matter, you are working in water, you are working in cow
Oh,
dung, or you are working in
okay.
like any environment. It's raining and you still need to do measurement, because
Okay.
it is recommended, like you don't do measurement in rain. But in this country, if you wait for rain to stop, then you will never do the measurement, because it's all the time raining.
Okay.
Yeah.
Okay.
So
Okay. We have to do
then,
all those
yeah,
steps. Yes. Yes.
yeah. So yeah, that's it. So no, this is very good, especially this RMS thing, because I this is first time I'm learning. I thought it's RMS output. I never tried to verify it, because when I done those block diagram that I was showing you yesterday, I just follow PS cut tutorial from a guy on YouTube, and I was
Ah,
just running them without logic. I was not like verifying result or anything.
okay.
Yeah. So this is good, really good.
Uh, I will try to run it with RMS. What it does is like here we have to take it as single voltage and we have to maintain it on RMS for
Yes.
voltage. But in the case of current, we can just take it as single phase current and we can match it. Okay, okay. Then
So for
we will
voltage, what
speed
you
up
need
it.
to do is it's
You
basically
need to
showing
take
three
it
phases
as
together, right?
three phase to single phase. Like that, I have to put on converter and
Yeah.
then I have to
Splitter.
take it
Yeah.
as single phase RMS and then I have to measure the values. Yes. Okay. Then what we are been doing is like at what instance the fault current happens. That is what we have been speaking, right? Here you can see this graph. I hope here
Yes,
you
I
can
can
see
see that.
this. Yes, yes. Here I will show you at what instant I have closed the circuit. Here I have taken out the fault current in 0.8 seconds. Just wait a minute. I will come back. Just wait a minute. Yes, at which instant I have created a fault? I have created a fault at 0.3 second,
Yep.
0.3 second. Okay, and I am just trying to run this simulation.
I think you put the fault duration longer than your project setting.
Oh, no, 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 I have kept it as. That is not
No.
an issue. That is not an issue. I'm just trying to convey you some message to at what instant the fault happens does matters in the amount of fault current which is happening here. Okay,
Okay.
here you can see this. My fault current is about 101 amps, right?
Yes.
Just take it as this is just an example. Don't think this much of this is a peak value. This is a peak value. Okay, this is an
Yeah.
example. Here you can see this. My peak value is about 101.450 when I
Yes.
have kept this as a 0.3,
Yes.
right? 0.3. Now I am just going to keep it as an 0.325. Okay, at the what instant I am just closing, I am just closing at 0.325. I am just
Yes.
rerunning the simulation. Here, can you see this? The difference?
Yeah. It is reduced. Yes.
It
A
has
lot.
been reduced of a
Um,
value, right?
why is that?
152. Why is that happening? That we have to know, right? There is
Yes.
something called as at what instance your fault is being happening in the system, and what is your X by R ratio does some things to this fault current. That is what we have to know in this, right? For
Yes.
that, I will show you PPT. Here you can see this
Yes.
row. Here you can see this. This is the simple equation which has been written uh, for the L and C circuit. Okay, I will show
Yeah.
you the C circuit. This is a simple L and C circuit. Sorry, R and L circuit.
RF.
Okay, RL
Yes.
circuit with the source. Okay, with the AC source. And this is for this circuit, the basic equation which I have got is like this. Okay, this is the base equation for this particular circuit. Okay, and
Yes.
after that what they have did is like they have took some Laplace transform for this particular equation, and then they have converted to what they have did is like they have took the Laplace transform. Why do we need to go to this Laplace transform is that we can solve the equation simply by converting this equation directly to this equation. What they used to do take is like this Laplace transform they used to do take, and then what they will do is like using Laplace transform they will convert this time domain equation to some S domain equation which will be in algebraic format. Okay,
Yes.
and then after that algebraic format what they will do is like after coming to the solution with that algebraic format, what they will do is like then again they will take inverse Laplace transform. Then with that inverse Laplace transform what they will do is like they will come back to again this time domain value. With that this is the equation which they have finally arrived after those calculations. If you want to know how this equation has been arrived. For that, I will show you an one book. I will also share this book if you are interested. This
Yes.
book is called Alan Greenwood, Electrical Transient in Power System. Okay, this book has lot of contents. Here you can see if you want to know some basic about a simple switching circuit, what does happens, and if you want to know some transients, if you want to know more about transients, here this book will be more useful for you. Whatever the doubts I used to have, we used to go through this book to learn some new things about the transient. uh,
Okay.
Here you can see this the traveling wave concepts will be there, and insulation coordination concepts will be there, and here you can see insulation coordination concepts will be there. Like this there will be this book will be giving you a lot more information when compared to the other things, so that it will be in a easy manner also to understand the things, so that I am referring this book. If you want to know how this equation has been developed, here you can see this simple switching circuit. Here you can see this is the equation which I have taken
Yes.
from the net, and the final equation which I have arrived is this one. This is the equation which I have finally arrived here also in this PPT. The only thing which is difference is like for Vm divided by R squared plus, for this they have taken it as an Im. Okay, I is nothing but what they have been saying is like this is the equation which tells you the fault current. This I is nothing but the instantaneous current which is happening on the system. Okay, at
Yes.
the instant we have created a fault now, this is the maximum current which is happening on the system. Here you can see this equation has been written with two parts, right? Im sine into omega t plus theta
Yeah.
minus pi, and the other part is like Im into sine of theta minus pi e power minus rl rt divided by l. Okay, this equation has two parts. One is like a constant part, or what we can see, what we can say is like this is an AC part, most
Yes.
predominantly this is an AC part, and this is called as an exponentially decaying part. Okay, this is an exponentially decaying part. Here, the omega t, what it does refers is like the frequency at which it is oscillating. Right now, here we have taken a sinusoidal source, right? AC
Yes.
source. For that, it is referred as omega t. Okay, and what this theta tells is like it is what the main matter which we are going to talk now. at what instant we have turned on the switch. Okay, at what instant we have turned on the switch, that is what it is telling. Here we will be having our, see, L and R circuit, and here we will be having some T. Okay, at what instant we are switching on this switch, that is what the matters. uh, that is what the matters. What is the magnitude of the current which comes as a resultant value? Okay, this is the thing which refers to the uh, at what angle your switch has been closed on the voltage, at what angle of voltage your switch has been closed, so that your fault current will be kept affected. What this pi term tells is like, here this is the h by r term. Okay, we have been talking about h by r, right?
Yes.
We have been talking about h by r, right? What generally h by r is like, tan phi equal to h by r. This is what we call it as impedance triangle, right? Okay, this is what we call it as impedance triangle. From the impedance triangle, you can see that tan phi equal to h divided by r, right?
Yes.
Okay, then when what we have to do is like, we have to put phi equal to tan inverse of h by r.
XL by R. Yes.
Okay, this is the value which will be kept in this particular equation, right? Okay, and then what it does is like, this is, as I said, this is an exponentially decaying component. Here you can see this exponentially decaying component only consists of the angle at which we are
Theta.
switching
Yes.
and the h by r ratio. Okay,
Yes.
this has the most impact on the fault current which we have shown on the PS cat.
Yes.
Okay. Okay, then what we can do here is like, here you can see this. When this term will be uh, when this term will be 1, that is what we have to know. When this term will be 1, mostly. Hello.
Yes, I can hear you.
when
Yes.
when this particular term can be a value, when this particular term can be a value, like 1 or 0, when it happens.
When we are steady state.
When not in a steady state, when a fault happens, this is what the two terms which will be happening in the system, right?
Yes.
What it does is like, whenever there is a fault happens in the system, there will be two components in the system. One is called an AC component, and another one is called as an DC component.
Yes.
Okay. Whenever the fault happens in the system,
Yeah.
there is something called as a DC component.
Yeah.
And from where this DC component comes into picture? From where this DC component comes into picture? Because we have been dealing with this AC system only, but where this DC part comes from?
The DC part comes from maybe the, the the capacitance of circuit.
Not from the capacitance of the circuit. What we can tell is like, the H by R ratio. There's something called as reactance, right? The inductance part. What is the nature property of the inductance?
Sorry, yeah, inductance.
Inductance part.
It stores the current. Yes.
Yes, it does. What it does is like, it naturally stops, or what you say, it does resist the change in current, right? It
Yes.
don't actually allow the current to change suddenly, right? So
Yes.
this is the effect has been created by this particular part called as H value, reactance part. Okay. Then
Yes.
what I want to explain you is like, here you can see this is the most important part. Here what we have been seeing is like, both the symmetrical, what we say, that both the AC component and the DC component will be added here, and then the resultant will be changed to this like this. Can you see this?
Yeah. Yes, I can see it. Yes.
Yes, here you can see this. There is something called as some dotted line, right?
Yes.
Some dotted line, right? This is the impact which we have been seeing here. in our PSCAD screen, right? At what instance you have been closing that switch. Here you can
Yes.
see this. Uh,
Yes.
I hope I lost my screen. I have lost my signal. Whether I am
No, you can I can still see it.
yes,
Yes, your screen is live. You can yeah, I can see it.
yes, yes. Okay, okay. Okay, and then the thing which is happening is due to the part called as this switching action when the switching action has been performed. Okay, uh, just wait a minute. Here you can see this. There is an there is wait a minute. Here this is the voltage waveform, right?
Yes, Sanisha
Okay,
voltage.
this is
Yes.
the voltage waveform. This is the instant when we are going to at some instant of voltage only we will be switching the circuit, right? At some instant
Yes.
of circuit only there the fault will be happening in the circuit. But when my voltage is zero, when my voltage is zero, since it is an inductive circuit, most predominantly our system will be an inductive circuit, right?
Yes.
Then what happens to our current? What happens to our current?
Uh, it it will have
Generally in an
impact.
inductance circuit, generally what is the nature of the current in an inductive circuit? We
Or
will be
you mean
saying
it will
lagging,
lead the
leading,
yeah, it will be
right?
leading.
In inductive circuit.
No, sorry, it will be lagging the
Yes, it
voltage.
will be
Yes.
lagging, right? Lagging
Yeah,
behind
capacitive
voltage,
will be
right?
leading. Yes. Yeah.
So that only the current has been here, started here. Can you see this? It is the
Yes.
negative peak of the current which is happening here. Okay.
Yeah.
And what is the instant we are closing? We are closing at the zero crossing of the voltage, right? At that
Yes.
time, what happens is like your voltage, your current is at maximum, negative maximum, right?
Yeah.
Okay. Then what we have to do is like we have to go back to this equation. We have to go back to this equation. Here you can see this. There is something called as theta value, right? It is the
Yes.
angle at which when it is the value at which when you are closing the switch, right? And this is the angle what they have been saying is like in this example what they have been assuming is like the h by r is infinity. Okay, h by r is infinity. Then what happens to our tan value, like phi value? What happens to our phi value? Tan of infinity, what we can say, it is 90 degree, right? It is 90. Okay, then this part will be 0 and this part will be 90, right?
Yes.
This part will be 90. Then what we will get is like sine 90 will be 1, so that we will get some DC part, right?
Yes.
We will get some DC part. This is the impact which has been created in this particular system. Okay, here you can see this, the fault has been happening at 0, t equal to 0, and the angle at which it is closing is 0,
Zero.
and the phi is like pi by 2.
Yes.
Okay, pi by 2. That is what the angle which is happening here. So that only the DC part has been arrived. Okay, at the
Yeah.
other instant where we have seen the voltage, here you can see this, this part, no, this part,
Yes.
this part. This is the AC symmetrical part.
Stay dependent. Okay,
Yes,
sorry
it is
for
the
yeah,
AC.
three phase.
Yes, it is a AC symmetrical part. Okay.
Yes.
Now, due to this happening, now the current now since the current is lagging, what happens is like this inductance comes into action, and so
Yes.
that there will be some DC component will be
DC
introduced.
component. Yes.
Here you can see this. They have shown like DC component, right? That
Yes.
DC component has been introduced in the system. So that what happens is like my resultant value will be shifted upwards, right?
Yeah.
This is the impact which we have been seeing in the PSCAD. Okay.
Yes. Yeah.
Okay. Then what I need to show is like this example. Here you can see this. There is no such scenarios. Why
Yeah.
means here we have switched the voltage at 90
Okay.
degree,
Yeah.
and then what happens to this equation now? What happens to this equation?
Sine 90.
Sine 90. This will be 90, and this also will be 90, right?
Yes.
Because the same scenario.
Yeah.
like
Sine 0
tan,
is 0 and then dash 0. Yes.
the whole term will be becoming 0. So so here you can see this, there is no such part as DC component.
Yes.
Okay. Okay, this is what it has been happening here. Generally, what we can say is like inference for this short circuit. What we can say is like there is two parts, like right. One is
Yeah.
non-decaying AC component, right? The part which
Another
has been
is
showing
decaying
here,
from.
right?
Yeah.
This one, this AC form. This is a
Yeah.
non-decaying one. It happens, right?
Yeah.
But other part which we have shown is which we have seen is like decaying DC component, right?
And same thing will happen even if I do like a phase to ground fault. Is that right?
Yes, yes, the same thing happens. Yes, it is for all the cases. It is for all the cases. At what instance you are the fault is happening, it does matters.
Yes.
Okay,
Yeah. Yes.
okay. And then the other thing which I have explained is like since it is an exponentially decaying component, what at the instance what happens is like at the time t equal to 0, we don't take it as 0. Let us say it is a small value like 0.001.
Yes.
Okay, at the time what happens to this L value? L will be higher, right?
Higher. Yes.
X value will be higher, right? And then what is the value of this E part? E power minus small value, which is much lower value.
Lower value. Yeah.
Much lower value. What happens? E power, for example, let us take the lower value as 0.002, like that. What we will get is like we will get some value, right? Near
Yes.
to 1 we will get some value. Okay, so that this DC component will be there, this exponential decaying component will be there at the instance of when the fault happens. Okay,
Yes.
as the time passes, what happens to this value of t? It is nothing but t is nothing but time, right?
Time. Yes.
What happens to this time? Time gets increased, right? It changes.
Yes.
Okay,
Yes.
when the time gets increased, when the time gets goes on, what happens is like this e power minus this value gets keep on increasing, right? Will keep on increasing. At
Yeah.
some
The
time,
time. Yeah.
what it does is like e power minus a larger value. Let us say something like e power minus of some larger values, for example 200 or 300. Let us say what happens to this value is like it does happens like a zero, it becomes zero.
Yes.
Okay, so that only what happens in our system is like as the time has passed, this decay component, this DC
Has
component
gone.
has decayed, has gone
Yes.
out. Okay, so
Yeah.
that the main part which I want you to know is like there is something called as an DC component,
Component due to
symmetrical component.
expire. Yes.
Yes, symmetrical component, and another
Yes.
component is called DC component.
Yeah.
Okay, and the total of this symmetrical plus DC, what we say it as asymmetrical component.
Yes.
Okay, asymmetrical component. This is what I want to
Yeah.
convey you. Okay,
Yeah.
the
I
general
get that.
information is like other information is like the presence of DC component makes the fault current wave shape envelope asymmetrical around the zero axis, right? That is
Yeah.
what we have seen here, right?
Yeah.
And the other thing is like higher the H by R ratio, slower the decay.
Good.
Okay, this is
Yeah.
what I want you to know. Higher the H
Yes.
by R ratio, slower will be the decay.
Yes.
Okay. This part we can see in the ETAP itself. Okay, ETAP itself. I will show you how
Yeah.
we can see this. I will close all these tabs. Okay, I will go to my ETAP screen. Here, just for your understanding sake, I have given a grid. This is nothing but a grid. Okay, power grid.
Yes.
Okay, I have modeled this power grid with 400 kV voltage and short
Yes.
circuit of H by R with some value like 26.
Yeah.
Okay, I have given some value for kiloamps also.
Yeah.
Okay, and then what I have did to the other example is like I have took the 400 kV same system I have copied and pasted here. But
Yeah.
what I have did is like I have kept the H by R ratio as triple nine,
Infinite.
nine,
Yeah.
nine, nine,
Yeah.
nine,
Yeah.
because we cannot
I.
keep it as infinity.
Yeah.
So that
Higher.
what
Yeah. You mean.
higher than value. Okay.
Yes.
Then what I'm just going to do is like I'm just creating a fault here.
Yeah.
Can you see this? I have created a fault here.
Yeah.
Okay. I have created a fault in this location also.
Yeah.
Okay, just what I'm just going to do is like I'm just going to run the simulation. Okay, I will just
Yes.
run the simulation. Yes, the simulation has run now. Okay, now just
Yes.
remember the name of the buses, which is bus
Yeah.
1,
Bus one and
bus
bus
3.
three. Yeah.
Okay, then we will go inside this plot. Here you can see this, there is something called as
Yeah.
plot.
Six one
I
three
will
six
go
one.
inside this plot. Okay, which buses we have to see? We have to see bus 1
Bus
and
one
bus
and
3.
bus three.
Okay. Bus 1, what we can do is like which bus has the infinite H by R?
Bus one.
Bus 1 has the infinite H by R. Okay. I will just compare those plots. I have selected those two buses and I will just show you how this waveform has been behaving. Okay. First I will show you the DC component. Okay. First I will show you the DC component. I have chosen both the buses and I am just going to select plot. Can you see this? Can you see
Yes.
the
So yeah.
bus
So
3 has some finite value of H by R, so it has
yeah,
been
it's
decaying.
decaying
Yes,
easily. Yeah. Yeah.
yes, but the bus 1 has an infinite of decaying
Yeah.
H by R
Yeah.
ratio, so it
Because
is
of the
not
higher
decaying.
expi. Yeah. Yes.
Yes. Then what happens to our final waveform, whether it decays or not?
Uh, which final? You mean the bus one?
Asymmetrical component, whether it decays or not, the fault current.
It will decay, but
No.
just in bus.
Yes, I will show you. I will show you. Now I will plot. Now here we have seen the DC component, right?
Yes.
Okay. I have said something called as there is something called as symmetrical component, right? Symmetrical,
Yes.
which is a
Yes.
constant waveform, as I have
Yes.
shown here. This
Yeah.
constant waveform,
Yeah.
yes,
That won't decay until the fault. Yeah.
until the fault has been here, right?
Cleared. Yes.
What
Yes.
I have do is like I will show you the AC RMS. Here, can you see this? This envelope has been not decaying at all. It is a
No.
constant point, right? It is a
Yes.
constant point. It is kept at the value. Here you can keep the hairline and see it is maintained at 39.5 Ka.
Yeah.
Okay, because this is an constant part.
Constant component. Yeah.
Yes, AC component, right? Then
Yes.
what I will show you is like the final part, which we say it as
Both.
asymmetrical component.
Yeah.
The resultant of
Something.
both
Some.
is,
Both.
yes.
Yes.
Yeah, I will show you. I have given the phase A. Can you see this? I will close all those tabs. Here, can you see
Yes.
this?
Yes. I
The
can see
bus
that.
which has an uh, decaying component has decayed, right? Here it
Yes.
has came down, but here you
Yeah.
can see this wave has been not been coming down. That is
Yeah.
due to
Because that DC component
has been
has a
high.
higher X by R. Yeah.
Okay, this is the importance of this H by R and fault current and all.
Yeah, I get that. I read somewhat similar a long time back in IEEE as well, but
Okay,
now I don't do IEEE based studies, so I never used it after that. But yeah,
okay.
I
This
remember
concept
that
is
top of
same
my
for
head.
this concept is same for all the cases. This concept is same for all the cases.
Yes,
Okay.
thank you for that. Yeah, that's great.
Yes. This is what I have tried to explain you. Okay.
Yeah, yeah,
Okay. Gokulji, can you take it from here? Can we have some 10 minutes or 15 minutes break? Then we can continue the
yeah,
session.
yeah. We will have
Uh,
10 minute break, no
10,
problem.
Yeah, yeah.
10, 10 minutes break. Then we will start it at 3:30. Okay.
Yes, yeah,
Okay. Okay. Fine. Gokulji, can you
yes.
take it from here?
Yeah. Yes, Venkatji, not an issue.
Okay. Okay. Yes, Himanshu. Himanshu, from here, Gokulji will take care. Okay.
Yeah, yeah, no
Okay.
problem. Yeah,
Okay.
that's great. I will see you in a few minutes. Bye.
Yes. Yes. Bye.
Hi, Himanshu. Himanshu, am I audible?
Yes, yes, I can hear you.
Yeah, yeah. So, shall we start?
Yes, please. Yeah, go ahead.
So far what Venkatji have explained was the concepts, the theories behind what is fault current and what is the significance of XPR ratio and what is basically what is PSCAR and what kind of things we are going to do in PSCAR. So that was the
Yeah.
basic theories behind it. So now we are going to look into source modeling and what are the calculations behind the source modeling which we are used in PSCAD. So when I say calculation, that is not a big deal. Just a basic formula, you can do it in you can do it in source modeling. So just a basic formula. We have some straightforward formulas itself to calculate the impedances for the zero sequence and positive for the positive sequence. Mohan, can you share your screen? Yeah, Mohan. Okay, okay, he's not available. Just a minute, Himanshu. Just calling Mohan.
No problem. Take your time.
Screen share பண்ணுங்க Mohan. நான் phone வாங்கினேன். Okay. Yeah, Himanshu, he is coming. He's coming. So we are going to see what is the calculation and we are going to verify our source model. So
Yes.
basically in PSCAD we have to verify the model. So that is most important thing.
Yeah,
Just
that's
like
what I
that.
was going to ask. Yes. How
Yeah,
do you do that?
yeah.
Because
So
every
just
model
like
has
that.
to be validated. If we do something and we just basically think like, oh, this is happening. Okay. You know,
Yeah,
then
exactly, Manchu. So we have to do it not only in PSCAD. You take whatever software you use, you have to just verify the model which you have correctly used or not. So
yes,
in PSCAD we have to do that. So that is one of the main important thing in PSCAD. Not only just giving some values, we have to verify the value whether it is correct or not, and we should have some reference value with us. So that reference value we have to get it from the client. So I will show you what things you have to get it from the client with respect to source and have to
yes,
model and have to calculate and have to verify that.
yes.
Yeah, so we can do it. Yeah, Mohan is in online it seems.
Is you know available? Right.
Yeah, yeah, yeah. I just called him. Yeah, 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 yeah. He is available right now. Yeah, thank you, Mohan.
Just give me some.
Yeah, yeah. So yeah, we can see your screen. So I just give my request control. Accept that. Please accept that. Yeah, that's enough. I can take care, Mohan.
Yeah.
Thank you so much, Mohan. So what we have to going to do is we are going to just create a new project and we are going to just simulate that. So that is important thing we are going to do. And before that, I have some thing to show you what values you have to get and everything. So Mohan,
Yes.
where is that the thing which I sent you, right? The calculation and so I have some pretty two things to open.
No, no,
Yeah.
I can't able to.
No, I need the just a minute. I will stop control. Yes, take that snapshot on Excel sheet. That's nice.
Which you send, right?
Yeah, yeah,
WhatsApp.
true. Yes.
This one, right?
Just, yeah, just download that and keep it in the desktop, so that will be easy for me to use it.
Sorry?
Yeah, download this and keep it in the desktop.
Okay. Interesting.
Both the Excel sheet and the snapshot.
Excel also.
Yeah, the Excel as well. Yeah, both.
Okay.
Yeah.
Yes.
Yeah. Okay. Okay. So yes, Inga. So I give a request control. Please accept it. So the value which we need for source modeling, it's I have just a snapshot. I've given you a snapshot of this.
Yes.
So you know what is the voltage level? Like we have two voltage level here. So we are going to model three sources. So totally three sources. Which
Yeah.
one is 400 kV? The main voltage is at 400 kV. There is a two sources, and at 220 kV there are two sources. So that is the meaning of that. So yeah, you can see like the two bus. There is an RAF, which is an there is an one substation. So we are going
Yeah.
to model that as a source, and there is
Yeah.
another substation which is Salaya Super. We
Yeah.
are going to model that as a source, and Ain Khalid Super, which is 220 kV. That is we are going to model as a source.
Yes.
So for modeling a source, we need two values. The fault
Okay.
current, the three phase and single phase fault current, we should know that. So this
For
thing
the
we
source.
should, yeah, for the source, yes. So the three phase and single phase short circuit, you should get it from the client, and
Yeah.
then the XPR ratio. So the XPR ratio also you have to get it from the client. So in our case, for both the substation, we have a same XPR ratio. Then we can use this XPR ratio for the two source itself. So
Okay.
that's what this snapshot is trying to tell us, right? For the RAF and for the Salaya super substation, there is 25 XPR ratio is equal to 25,
Yeah.
and these three phase short circuit and single phase short circuit they are given. So this value is more than enough to model a source.
Okay.
Yeah. So yeah, we can go for the calculation, then we can
Yeah.
go for the PS cal.
Okay.
So I have calculated. I have Excel sheet for us.
Yes.
For that. So first we can calculate the three phase short circuit current or a three phase impedance.
Yes.
So so there is a standard, right? IEC 60909. So have you ever heard of that?
Yeah, I heard of it. Yes, but I
Yeah.
never used it.
So that is basically for calculating a short circuit current. So
Yes.
very basic on that. So IEC 60909. So this is the snapshot in that IEC 60909, page number 27. If you just go to that page number, you will end up with this document or this wordings you can see. So here what they are trying to say is like if a three phase short circuit in accordance with like there is some figure which only the initiator like so which only the initial symmetrical short circuit current IK double dash. So you
Yeah.
can call it as IKQ or IK double dash. So we can take that, we can take our snapshot and we can check. So
Yeah.
this is IK double dash.
Yes.
So the client always will give you the IK double dash, which is the symmetrical fault current. What Venkat ji have taught us, right?
Yes.
So there will be a symmetrical short circuit. So 39 and 43.73 is a symmetrical short circuit current. So for calculating for calculating the impedance, we have a formula for it. So for the this is only used for three phase short circuit. Here also they have given, right. Then the equivalent impedance ZQ of the network positive sequence short circuit impedance So here they have not mentioned zero sequence. So do you
Yes.
know when my system will have a zero sequence impedance, or when my system will have zero sequence current?
When there will be a phase towards fault.
Is exactly correct. When my system has an ground fault, or any phase to earth or LL to earth or single line to ground fault, if my system has that, then my system will experience a zero sequence short circuit fault current. So,
Yes.
but here, when my system will have a positive sequence fault current, whenever there is a fault, if there is a fault, then there will be a positive sequence current. So, damn sure I know that. So in three, yeah, that IEC 60909 clearly said that this or this formula or this calculation is only used to find the positive sequence, not for zero sequence. So we should not mislead that this is we can use for positive sequence and zero sequence. No, only for
Okay.
positive sequence you can use this formula. So
Yes.
you get a good understanding on why we are going to use only this for three phase. So
Yes,
you have an
because there's
understanding,
no
right?
ground fault. Yes. Yeah.
Yes, exactly, exactly. Okay. So we can first do the three phase fault current, and we can go for a single SLG fault. Sorry, I'm sorry, I took that. So description, value and unit. So this is C factor. So we have a separate section for you for what is C factor and what is the significance of that. For time
Okay.
being, just listen this. Like I will let you know what is C factor, and
Yes.
by this end of the class, I will like share a snapshot of what is C factor and what are the typical values for C factor. I will share that in our WhatsApp group. You can very well check that. On the
Okay.
later classes, we can discuss what is C factor. There will be a separate session for C factor itself. So,
Great.
yeah, this C factor 1.05, where I have took, or I can just show you the reference. So here itself they have said, right, 1.05 per unit.
5 per unit. Yes.
Yeah. So generally, if there is a fault, there will be two voltage, right? Like one is pre-fault voltage and post-fault voltage. So there will be
Yeah.
some terms like pre-fault voltage and something like that.
Yeah.
So
Yeah.
what they are trying to say is, when there is a fault, my system will there are some chances my system will have 420 kV, which is 400 into 5%.
5%. Yes. I get that. Yeah.
This 39, what they have assumed is when my system has a 320, 420 kV, then it has 39 kilometers as a fault current.
Yes.
So yeah, similarly for here also, when system has
Okay.
a 420 kV and there is a single line to fault current, the
Yeah.
maximum fault current is 43.73 kilometers.
Yes.
Yeah, so do you have any doubt up to this?
No, not at all. It's
Yeah.
clear.
So yeah, so this is the exact thing what I have used in our calculation, which is C factor as 1.05. So we know what is the voltage. Like U1 is the voltage, like just like that. There are some different terminology, but U1 is
Yeah.
the
Terminal
system
voltage.
voltage.
Yeah.
Yeah, terminal voltage, system voltage, 400 kV. Then IK double dash, like as I said, that is that's the symmetrical fault current, and that is 37.63. So this is RAF, right? You can see the name of that,
Yeah.
the sheet.
Yes. Yes.
RAF. So first sheet is RAF. So I have taken from 37.63. So this is the value. Like,
Yeah.
yeah. So RAF. So I can change that to 39 itself. Right? Just give me a minute. RAF. Yeah, 39. I can change this as 39. But in our case, it is 39, right?
Yes.
Yeah. Yeah, that's good. So 39 kiloamps. So the XPR ratio is 26. Where I got the XPR ratio here, like 25. So we can change this as 25 itself. So
Yes.
we can go to the calculation and we can change that as 25. Right, we can. So this is just on root 3 because we are going to use on root 3 over here. So in the formula.
Yes.
So
Yeah.
that's why I've used. So we are going to find the ZQ. So
Yeah.
ZQ is equal to C factor into 400,
times.
or this is 1.05 into 400 divided by root 3 into 39 kilo amps.
Yes.
So here
So that's
I've
that.
used it.
Yes. Yes.
So the same thing we have used, and we got the value as 6.21. So
6.21.
yeah, we got the ZQ. So
Yeah.
we have only Z. We need R and X. So that is the exact thing we are going to do in the source modeling. We are not going simply going to give the impedance. We are going to give the R and X separately.
R and X
So
of the positive sequence. Yes.
yes, exactly. So we have only the impedance, but we need the R and X resistance and the impedance separately.
Yes.
So to find that, we have a formula to find this. So X is equal to Z divided by root of 1 plus R by X whole square.
Why is saying if
So
RQ and XQ is known, so what is the RQ and XQ? One is divided by your X by R.
yeah, your X by R just inverse of X by R by Q.
Okay. Okay.
So the second step, we are just going to inverse this.
Yeah. So that's
So,
0.04.
so 0.04, and
Yeah.
we have just squared this like 0.04 into 0.04. Like
Yes.
we have done step by step,
Yeah.
and we have just add 1 into it. So
One.
that's the formula,
Yeah. Multiply
and
top.
we have just square
Yes.
root that. That's it.
Yeah.
So you now you'll end up with the x value. So you got the x, which is 06.2128,
Yeah.
and you know x, you know z. So you can simply you can find the r, because we know x by r ratio is equal to 25.
Yes. So that just multiply by that value basically.
Yes, exactly. So you can just like that you can get the R value. So yeah, just a simple calculation. Like the calculation doesn't need a big theory. Like just a simple calculation.
Yeah.
So
As
this
long
is
as you
this is
have those values. Three
yes.
phase.
As long, yeah, if you have the
Yeah.
XPR ratio on the fault current, then that's just a matter of fact. Like you can do it just in minutes, right? So
Yes.
that's simple. So right now we know the three-phase fault current, or the positive sequence current. We know that positive sequence current, but the negative, but the zero sequence impedance also we should know that. For that,
Yes.
we should know the single line to ground fault, right?
Yes.
So here comes the single line to ground fault. So SLG, like single line to ground. So the
Yeah.
formula is like, it's basic, like we would have studied in our college days, right? So to find the single line to ground fault, 3 divided by C factor into Z1, Z2, and Z0 is the sequence current. Like Z1 is the positive sequence, Z2 is a negative sequence, and Z0 is the zero sequence.
Zero sequence. Yes. Remember that here.
Yes, so we would have studied in our college days. So the EA is the line to ground RMS current. Like that's not a line to line, that's a line to ground. So which means 400
Current
divided by
or
root 3.
voltage, you mean? Yeah. No
Yeah,
current. Yeah.
yes, voltage.
Yes.
So 400 divided by root 3. That is your EA, or that is your voltage, 231. Like round off, if you round off, 231 or 230.94. So the same
Yes.
factor you can take 1.05, like the same thing which I have took
Yeah.
from
From
the
the Excel. Yeah. From the client data. Yes. And
so
then current.
this is 43.73.
Yeah.
The thing which we have, it is 43.73. Yeah, and the impedance is we can take it from the like you can take it from the here itself,
Yeah.
because this is
So
the
that's
positive sequence, right?
yeah.
Yeah, so you can take it from. That's why I just went to first for three phase, then I went to single line to ground fault. Yeah,
Then
so
you
we
consider
can
same for Jet2.
yeah, for positive sequence and negative sequence are same. So that's what I have considered.
Right.
So
So you can assume that same as a positive.
yeah. I just like I can assume that, and I can continue my calculation. So
Okay.
this is the formula. So if you want,
Yeah.
so you have everything, right? You have
Yeah.
this
Yeah.
Z1 and Z2. You have the
Then
fault
we
current.
can
You have the C
calculate Jet no.
factor. You have the EA, which is like 400 by root 3, and 3 is just a constant, you know the value, just 3, and by just multiplying it, you'll get up with end up with this value, like
Yeah.
4.199.
Yes.
So this is the same thing we have done.
Yeah.
So now the XBR ratio, which we have known, the XBR ratio is 25. So
25.
we have to give 25. So the XBR ratio is 25. Here, then this is also a simple calculation. So we know what is R or Z is equal to root of R square plus X square, like that. We know that formula. So using that we can find it. So this is 25, and X by R is equal to 25. Then X is equal to 25 times of R, right?
Yes.
So that's a simple like formula. So we know the formula, like R is equal to square root of R square plus X square.
X squared. Yes.
Yeah. So we know the R, right? So X is equal to 25 R. So
Yes.
here you can rewrite as Z is equal to square root of R square plus 25 R square.
Yes.
Am I right?
That's right.
Yeah. So yeah. So the same thing I have rewritten as 25 square is the uh, 25 into 25. 25 into 25. So you'll get 625 R. Then
Yes.
here 1 R square plus 25 R square. So that
Yeah.
is the formula, right? R square plus
Yeah.
25 R square.
Yeah.
So you can just like 625 plus 1, then you can just square root that. So you'll get 25.02, and if you want R, so you can just divide by um, say you can divide to this value, then you'll get what is the R.
Yeah.
So the R is 0.1679,
Yeah.
and the X is equal to 25. Like it's 25.
Yeah.
So X is equal to
25 time
25.
R. 25 time R.
So this is just a simple calculation, like you don't need much time as well, right? So just a simple calculation you can do it.
Yeah.
So yeah, we have the calculation for the RAF substation. So uh, we have this calculation with us, so we can model this source now. So we have to
Now,
model this. Yeah.
yeah. Now, when your client says at the end 3 column R naught per unit, X naught per unit, B naught per
Yeah.
unit, what these values are?
Actually, these values are these are the impedance values, but this is in per unit.
Right?
Yeah.
No, in the
Yeah,
ohm.
but I'm sorry, what's that? No,
I
no,
said,
that's not an ohm. That's in per
yeah,
unit,
that's
right?
per
So
unit.
this,
But you can't
yeah,
convert or
but
use these values.
yeah, we want in ohms, right? So in source modeling, we have to do in ohms. Like in
Okay.
PSCAD, you can
Yeah.
you that will ask only in ohms. So I can just
Okay.
open a source.
Yes.
I can just go to this master library. I can just open that. So more on sources. So this is the source we are going to look at. So this is the source, the third type. So R plus X, and if you go to positive sequence, like C, can you see the ohms?
Yes.
So this is asking in ohms, but we cannot directly give in per unit. So we don't need to
Okay.
unnecessarily give another calculation for converting per unit to ohms. So just like
Okay.
that, we
Easier
can use.
easier to do is this, right? I get that.
Yeah, yeah. So that will be not so much time consuming. So just like that, we can
Yeah.
calculate and can give it.
Okay. Good. I understand.
Yes. So we have the calculation. Now we are going to do the source modeling in PSCAD. So we can go to this PSCAD. We can have a separate project for us. So separate file. So you have to just go new, and yeah, one thing, you should not use any space over here in this name. You should not
Yes.
use any space. Like I
Yeah.
think so. You know that, right?
Yes.
Yeah. So like I know here check. So so let it be.
Or you can't use the special symbol as well.
Okay. To let it be. See, source modeling. We are going to look. So I'm just going to trying to so let us take the source which we are going to model, and we can
Yes.
just copy this and we can paste it like simple thing. Yeah, paste it. Just Control R will rotate this. So just try to zoom rectangle. So this is the source we are going to model. So just double click this. You can give some name to that.
Yeah.
So let me give some name, like let it be two. So you know what to do for the base MA. Let it be 100 MA for our
Yes.
convenience. So let us
Convenience.
not
Yes.
change it. So the base voltage is 400. Like I have a
Yes.
question for you.
Yes.
Whether it should be 400 or 400 into 0.5 percentage 420. What value should I give there? Like whether it is 400 or 400 into 5 percentage of that.
I should give you the 400 because the 425 will happen after the fault. Is that right?
Yes, exactly. So the system voltage will not change. So the base voltage is 400 kV.
Yes.
That's good. The base is 400 kV, and the base frequency is 50 Hz. So our
Yep.
system is 50 Hz. So let us
Yep.
give the 50 Hz. And yes, it is not the infinite. It
Plus.
is
Yeah.
not. So it's not infinite. So on the zero sequence differs from positive sequence. Yes,
Yes.
of course, because we have two separate values for single line ground fault and three phase fault. If three
Three phase.
phase fault and single line to ground fault are same, then
Yeah.
we can conclude that both sequence current are same,
Same.
or sequence are same. Yes. So I have to just give S16 here. So the impedance format is R by X value. Let it be that. So that is so simple, and we
Yeah.
have some straightforward calculation for that also. So that will be so simple for us. So
Yes.
this is configuration page. So we can move to the positive sequence impedance page.
Yes.
So yeah. So in PSCAD, the units are a bit tricky, and you have to follow this unit. So you cannot
Okay.
give in micro ohm or milli ohm. Like if it's an ohm, just try to give it an ohm itself.
Oh. Yeah.
Don't take that risk. Like if you want to, you can just add an M, like will be milli ohm or something like that. But don't take that risk. Just give
Yeah.
as it is. If it's asking ohms,
Yeah.
if you get the value with micro ohm,
Yeah.
convert to
Convert.
ohm and give.
Yes.
Yeah. So that thing you have to be caution on that. So if you're working in PSCAD, that should be a small tricky part. So
Okay.
we can go for the resistance, which is we can take it from our calculation. This is
Yeah.
positive 6, so you know where to take it, the resistance. So you
Three
have to
phase.
take it from here.
Yes.
So yeah, just copy this and you can paste it. So PSCAD will give this. So you can just copy from here and
Yeah.
you can paste it over there. So like simple thing. So this is resistance. So select all of this. So yeah, this is resistance, and reactance will be greater than resistance. That's of course we know that.
Yes. Yeah.
So we can go to the that thing, and we can just copy that. This is the react. We can just copy this and we can paste it here. Select all this. So the positive sequence is over. Next we can go for the zero sequence.
Zero sequence.
So zero sequence, you have to take it from the single line to ground
Got
fault.
it. Yeah. Great.
0.16967 is the single line to ground fault. So we can just
Yeah.
take this and we can paste it on the R resistance.
Another is 4.1963.
You can just copy this and paste it. So now we have done this. Okay, let us save this. So if anything happens, if it close. Yeah. So now we have given. So you can see, right, the values. You can see it. If you don't
Yes.
want to see the values, like there is an option like
You can just
just give it no.
yes.
It will just go away. So
Yeah.
this will be fine. So so we need a bus and we need a fault to verify it, right? So
Yes.
now we have done with the source modeling. Only two things we have to do. We have to externally add this. So yeah, we can go for the components over here. If you go to this components page, then you'll get this integer constant and real constant. So
Yeah.
let me take the real constant itself. Yeah, you can just paste it here. Just rotate this, and you can just connect it. You can connect with the wire, or you just connect it. So that's okay.
Directly. Yes.
Yeah, just copy this, and I'm going to paste it over here. It's connected. So this is what voltage I have to give, whether 400 or 5% increase of 400.
The increased one now.
Exactly. Yeah, exactly. If you want to match the fault current what they have given, you have to
Yeah.
give 420, like which is the
Exactly.
5% increase of.
Yeah.
Here let it be 0. So we are not going to give any phase shift or anything. So let it be 0. Yeah. So the source modeling is 100% completed. But
Yeah.
we have to verify it, so that is important. So we have to introduce a fault. So before that, let me connect a bus over here, and I have to rotate this controller will do it, and you have to place it in between and drop it. Yeah. So you can take this wire, or just
Yes.
click Control W, you will go into wire, or you can use it. Just place it over here and place it at the one end of the bus. Yeah, that's it.
Yes.
So it just connected. So just go to the bus and just give the base kVA, which is 400 kV. So that is the system voltage, right? So we can just give 400 kV. So in bus, this is one of the thing you have to give. That's it. Only you can give the base kV. So that is okay.
Is that matter if you don't put that base KB same
No.
as the previous one or just leave it blank? What
Yeah,
it
you
will
can
do?
just leave it blank. Leave it blank. No, nothing will happen.
Yeah. It's just to
You can.
basically identify for yourself or someone who's looking your
Yes.
model. Yeah.
Yes, exactly. Just for identification purpose, like it will not
Yeah.
affect the results. So you can
Yes.
just leave it blank.
Yeah.
So it is done. So we have to give the fault and we have to check it whether we can get the fault current right or wrong.
Okay.
So to take the fault current, yeah, just go up. That will be called more on breakers and fault. So if you go into it, you can get this. So this is the fault current. So
Yeah.
you can just copy this Control V, and you can paste it. Control W. So the modeling is over. So we have to give the three-phase fault and we have to check it. So to check it, we need some data labels and we have to go.
Yeah.
So let's go into this timed fault logic. We can get some value. Let it be 0. 0.3 and let it be for 5 seconds. So I'm not going to clear the fault. So that is the understanding of that. Then the fault. So first, so this is external, like this is internal. So let it be like that. So we can go, we can straight away, we can jump into fault type. Let it be three. First, we can simulate the three-phase fault.
Yes.
Three-phase fault, and if you want to give any fault resistance, you can use this tab, and you can give this.
Otherwise, leave
So
default.
yeah, you can just like leave it default. But if you want to give any fault resistance, then you can use it.
Okay.
So, next fault current names you have to give. So we can give some current name. Like let me give I. A. So the second one is ID, and the third one is IC. Let it go. So we have done with default. Next, we have to do the data label and the work. So
Yep.
you have to use the data label, and to view for viewing purpose, you need an output channel.
Yes.
So we need a wire to just connect both of them. Name we have to give. So let us give the same name which we have given in the fault current. So
Yeah. Capital I.
Next, we have to give some name for it so that we won't end up with confusion.
Yeah.
So, let me just copy this.
Yeah.
This will be IB. So this is B phase.
Yeah.
You can copy the same thing we have done.
I see.
IC, yeah. This will be C phase. This is for our understanding. Oh, sorry.
Yeah.
This is for our understanding. You can give whatever name you want. So you can see the plot. So right
Yeah.
click and graph meter control.
And grab it. No.
We can increase our canvas setting, and we can increase our page.
Yeah.
Let it be here. So now we have to verify our model. So whether we are getting the same fault current for the three phase.
Yes.
So just try to save this and we can run. So just play this. So there is no error, so that's good.
Yeah. It's always good.
Then we have to spend time for that. PSK will not even say what was the error in a clear manner. Like it will give some its own terminology, so we have to find it.
Yes. True. Yeah.
So
For
three
that
phase
you need
when
to be
yeah, yeah.
knowing little basic basic thing about software. Otherwise, you won't be able to figure out.
Exactly the same thing I felt on the first day which I've used to learn this PSK. So that was always the toughest thing.
How long you been
So
using this?
uh, for 2 years, for more than 2 years.
Okay, good.
So since this is a three-phase fault current, so all the phase will be equal. So we
Be the
can
same.
check only the
Just the one. Yes.
100, right? Okay. So yeah. So can you spot any error in this so that we can make like so Venkatji have said something right. So
Yeah,
can
this
you
is a
spot
peak
any error?
current. Yeah.
Exactly. Yes, exactly. So what
The
we
another
have to
thing I
do?
want to the another thing I want to ask one small question on this, because how do I know? Because you show me that if you change the occurrence of fault current a particular time instead of 0.30, 0.40 or something, it can change the magnitude,
Yeah.
because of how it behaves. So if I am going to verify this model, how exactly
Yeah.
you know that you will get the exact magnitude on point 0.3? Is that written in a customer sheet or somewhere?
No, no, no. Okay, that was a good question, and I will explain that. So I'm so
Okay.
happy that you asked that question. So like I was about to explain you, but that's good. So I have this is a voltmeter to ground, right?
Yes.
So I have just connected this, and let me see the what's the voltage.
Yeah. One more
First, we
channel.
can see what is the voltage. I have to just copy this and I have to paste it over here, and
Yeah.
let it be.
You want to give the same EA.
I have 3 and 4.
Yeah.
Let's give we can give it
I done these things without logic, just randomly. But now you are
a.
explaining by the concept, so it's another, good
So
overview
what
for
we
me.
have done, no, what we have done at preliminary stage, that was great. Seriously, that was great. So it's good. So that's why you can easily learn the PSCAT quickly. So otherwise, even this session will have 2 days for just for source modeling to explain all those things.
No, it's not about me for like creating these things and making these things. Once you show me, I am engineer, I can do that. It's not a big
Yeah,
deal.
yeah, exactly.
Maybe for others, but not for me. But
Yeah,
the thing is, I am more interested in like concept, like you show me how you calculate those sequence component and how you put in there. That's really cool.
yeah. So that is important. Like calculation always matters. So that is most
Yes.
important. So let me keep the voltage over here so that we can easily see it. So
Yes.
if you go to the zoom rectangle, you can just have a clear view on the selected portion.
Yeah.
And, yeah, so I have just given this voltage. Like before that, let me off this, or let me give us say 5 seconds. Give this. So and let me run up to 1 second. It will be defaulted to be on 0.5 seconds. So let me do 1 second. This is so this is the voltage waveform, right? This is the voltage waveform. If I want to zoom a particular portion, I can just like click here and I can drag this, and I can zoom a particular waveform. So
Yeah.
let us see only one phase. So let us see only the A phase.
Yeah.
I want just there's a tick mark, like I have to give the cross
Yeah.
mark, then it just
Yeah.
go up. So you can see there is a zero crossing, right? So this is the zero line,
Yes.
and at 0.3 is the zero crossing.
Yes.
So and at 0. Uh, say at 0.0315,
That's not zero
it is the
crossing.
peak value. That's
Yeah.
not a peak. That's a positive peak value.
Yeah.
So based on the switching actions or based on the switching instant, my current may change. So that the exact thing what Venkatji have told.
Yeah.
First, at the first he have kept at 0.3, which is at zero crossing. You can
Yeah.
see the voltage just went to peak.
Yes.
Yeah, but at next instant, he just closed the breaker at this voltage peak,
Yeah.
and the current was minimum. Like it was not a maximum, but it was minimum.
Yes,
So
I get
based
that
on
now.
your switching events, yeah, based on your switching events, your fault current may change. So that is important, and that is the only thing you have explained equation, right?
Yeah,
So yeah, so in that equation, that angle is equal to pi by 2. So at pi by 2, which is 90 degree, right? This
it
is
all.
90 degree.
Yeah,
So at
yes.
90 degree, if I clear any fault, then like I don't get the worst case. I'll get the favorable case, which is lesser the fault current.
It is easier to see in the graph. He was explaining the equation. It was,
Uh,
and I understood that, but like I asked the question, now I can see why that's the case because of the crossing here
this
visibly on the
this
graph
is
here.
this is all about zero crossing and the peak value.
Yeah, yeah.
So
So for instance, if I want to keep another value, so I can easily put like 0.320, 0.340, instead of
uh,
another value. Yeah,
instead of 0.3, you can just go for 0.030
yeah,
320. Then that's
yeah.
of course the zero crossing.
Yes, I get it.
So if you want to just like zoom, you can just click and you can just drag this, so you get a clear view. Like at 0.3, it is just a zero crossing. So it will not heal. It will heal the worst case.
And how do you justify this voltage? Again, the way you are getting the peak here is basically what we have input 230 kV
Ah,
divided
so
by root 3 multiplied by root 2. Is that right?
exactly, exactly. Like we have 400 kV over here. So 400 by root 3 into peak. So into root 2.
Say again, 400. No,
Ah,
we input 230 kV, I think, in this one.
no, no, no.
No,
This is
sorry,
400.
425. Sorry,
Yeah,
420. Yeah, sorry, 420, not 230. Apology.
so divided by root 3
Yeah,
into
and
root 2.
multiplied by root 2. Yeah,
Yes.
yeah. This is very important because I was confused when I was creating this.
Okay.
You know.
Okay. Yeah. Yeah. I can understand. Like this is this kind of basic thing which PSCAR will always don't.
No, it's yeah, it's good to verify the answer because if I want to know like what I modeled is okay or not, then it's really important.
Yes. Yes. Of course. Of course. So model verification is always the important thing in PSCAR. So you should have you should verify that. So
Yeah,
which is 342.920. So
yeah.
you
So
can
that's
you can get
3.928. Yeah, that's right. I just calculated it. Yeah.
good. Good. Great. So we can do the fault current at 0.3 we can do it.
Yes.
Zero.
Great.
Okay, then we can just simulate this, and again we have done the mistake. We have to include the RMS over here. So,
Yeah. Otherwise, it will spit out peak values.
for the RMS, you just go to main and the main library, and you have
Yeah.
to just
Go inside a meters. What
meter.
you say? Or on meters. Yeah.
So
See, I
you
am
should
learning
simulate
now.
this.
Yeah.
Okay, that's good. Like we can learn together. Like, that's good. So yeah, this is single phase meter, Himanshu.
Yes.
So it's not
Yes.
three phase. So if you're using it, you have to make sure that the IAIB should be a single phase thing.
Yeah. So you need to give one by one. One by one.
Exactly. So I have to
Yeah.
delete this one.
That's the benefit of learning from a user, same as me. Then you tell
Mhm.
me something because if I go to PSCAT, for example, or if I go to someone else guy and like give me training who are like supposed to be a PSCAT distributor or something, then what happens is you basically end up in like sales pitch. They try
Yes,
to just
exactly.
show you the capability of software, and I'm not interested in capability that I already know. I am not
Yes.
interested in like that kind of stuff. Yeah. So yeah, it's really good.
That the thing we have to know is like the basics on PSCAD. So if you know the
Exactly.
basics of PSCAD, we can do
Yeah, you
whatever
can
we
do
want.
anything. Exactly.
Yeah.
Exactly. Yeah,
So
that's
the
right.
thing,
And
so here we have used the RMS meter.
yeah,
So there are something you have to look into for RMS meter. Like this should be in digital. I'll let you
yeah,
know what is analog and digital. But first we have to like we can verify the model.
yeah,
So you have to give to as a digital.
yes,
So just give digital, and the fundamental frequency is important. So we have to give 50 hertz. This is
yes,
very important.
yes.
It
And
random
that's
or like default
yeah,
it will take 60 hertz.
Yes.
but
And
you
then
have to
answer
give
will
it
be
50.
different, of course.
Yes, exactly. So yeah, that's it. That's it about RMS. You can just copy this and you can paste it and you can use it anywhere you want.
Yeah.
So, now we are done this. So I think so everything is over. We can simulate this. Yeah. No error. That's good. So you'll get. So let us concentrate only on one phase because this is three phase, right? So we can just concentrate one phase.
Yeah.
So we need a fault current. So we can just take this. Take this. Let us. So okay. I have a question for you. So
Yes.
from where to where I have to measure to match the fault current which they have given.
At the
Whether
occurrence of fault until the clearance of fault.
like from 0.3 to 1 or from 0 to 1 or anywhere between 0.6 to 1.
I think we need to do from 0.3 to 0.6.
No. Like this is peak value, right?
Yes.
But the given data was a symmetrical fault current. It is not.
Yeah.
Yeah. So you get the point, right?
Yeah. It's right from the beginning of the signal.
No, you have to measure from 0.6 because this is the steady state. This is the asymmetrical value, right? This is the asymmetrical value. So this is peak value. I don't want the peak value. I want the symmetrical value. When I say ik double dash, it
Right.
is in
Sorry.
symmetrical.
Excluding the DC component. Yeah. Get it now.
Yeah, exactly. You got the point. That's good. Yeah. So you have to measure. You have to check from where the steady state starts. So you have to just click and zoom it from where the steady state starts. So from 0.6 I can measure because from 0.6 it is steady state. The curve is not just like there is no oscillations, right?
Yeah. Yeah.
So yeah, that's why that's why I asked that question. So
Yeah.
from 0.6 you can do it because that's the steady state fault current. Like that's just ik double dash or symmetrical fault current.
Yeah. You're not interested in asymmetrical part. Yeah.
Yes, exactly. So the x marker should be 0.6 and the y marker should be 1. So let it be 1.
Yeah. For the duration of the run.
So 39.061. So we can check what was our so 39. So
Yeah.
we can match this, right?
Yes.
We can do it perfectly. So 39.061 and 39 were somewhat close, so we can match it.
And would you do the same matching for a single phase to ground as well?
Yes, of course we have to do it. So we have to change the single line to ground fault. Let it be on the A phase, the faulted
Yeah.
portion,
Yes.
so that we can easily see that. Fault type, let it be no and let it be no. The B phase. Yeah, just do okay and we can simulate this. We have to save this and we have to simulate this. Yeah, no error. Here also there are some like there are some oscillations, but yeah, we can measure from 0.6 itself. So if you want to measure, you can go from 0.8.
0.8.
So
Yeah.
let me go to 0.8 because that is the steady state we can do it.
Oh,
It is 43.74
yes.
and can do it. Yeah, 44, right? 43.74 and 43.73. Like
Yeah.
we can match it.
Yes.
So you're able to get this right, Himanshu. So what we are doing and why we have to do this.
No, I understand it very, very well, and I will practice it. The only thing I want to ask, like, see you trying to verify the source and source impedance. I get that, but this is the only thing you verify before building your model or in your model, or is there something you also verify?
Uh, we have to verify each and every model in your system. So if you are going to model a OHL, you have to verify it. If you,
Okay.
yeah, this is the
But this is
exact
only
thing.
about source verification.
Yes,
Is that right? I'm
exactly.
saying.
Yes, exactly.
Yes. Okay.
When you come under OHL, like you have to verify this value. This value are given by the client itself. This
Yeah.
R and X and B.
Yeah.
You have to match this value yeah, that kind of different. We will let you know it once we are going to OHL
Yes.
modeling.
Yes.
Like
Yeah. Yeah.
tomorrow we are going to discuss on that. So I'll
Yes.
let you know how to model, how to verify your model.
Good.
That is always the important thing in PSCAD. So you have to verify that.
Yes.
Yeah. So far, okay, fine. I just want you to understand the mistakes. What generally we used to do, like let it
Yeah.
be analog. Let it be
Yes.
analog. No, not this one. Let it the A phase be analog. So that's the part we are going to discuss right. Be analog. Mm,
Yes.
this and I have to run. Yes. So you can see this right. So the difference between analog and digital.
Yeah.
So
Just the way
yeah,
it shows you the waveform. Is that right?
yes, exactly. The top and the bottom point it will just point out and it will show. That's it. Like
Yes.
there will be some difference. Yeah, the difference between this and the instantaneous is it will just take the top and the bottom point of the waveform and it will just show it in plot.
Show you
Like
the oscillation. Yes.
yes, exactly,
Yeah.
exactly.
Even
So
even even when it was having in a symmetrical way, so the digital graph was showing just a steady state line just to show like there's no oscillation, and here is showing frequent oscillation left right. Yeah, I get that.
exactly. So here also you can find out the steady state because the oscillation is not it just damped out from here
Yeah.
to here it just damped out. So
Yes.
you can.
Yeah.
So
Like
the
it's
another
easier to judge in another way, in digital way. You know.
yeah. So the another common mistake is we will set this as an digital, but
Yeah.
we will don't change the frequency. So that is one of the common mistake we used to do. So let
Yeah.
me do that as well. So 60 hertz is the default thing. So I just save this and yeah. So the
Yeah.
same thing will get like analog. So
Yes.
I have kept the digital it seems, but the frequency I've changed to 60 hertz. But based on the 60 hertz, the calculation will be different. So the
Yes.
common mistakes are these are the common mistakes we used to do in RMS. So we shouldn't do that because we have to verify the model. So like these mistakes we have to avoid that.
Yeah.
So, Himanshu, do you have the PS card with you? The
Yes, I have
no.
the trial one. Yes.
So no. I'm talking about the crack version. Do you have
No,
installed
no,
it
no.
or?
I don't. I know I don't have it. I was trying to look yesterday, but I didn't get anywhere in a good way. So you got any mean of downloading it, or you have a copy of it?
Fine. I don't have it, but I'll ask Venkatji and I'll try to ask with Venkat and I'll share it to you.
Yeah,
So,
that would be
so
great. You can send it to my personal email.
because
Yeah.
because we are about to give you some two assignments and that's why I'm asking that.
So the two assignment I cannot do in the trial version. I think I can do it.
Yeah,
No,
of
because
course you
it's
can
just
do
a,
it.
yes.
Yeah, just an two or three plots, so you can do it, not an issue. But
Yeah.
for the future go, that will not be that will the future
Sufficient. Yeah.
the free version
Yeah.
will not work.
Yeah. Yeah.
That's fine.
What I will do is because this is weekend, so I'm not working. So I will again try tonight, maybe looking some cracks. But if I don't get it, then that would be great. If you can ask Venkatji to send me something.
Yeah, I will do it,
Yeah.
not an issue.
Yeah. And this workshop, I can, this bus system, I will watch the video again and I will try to generate same result. And if you want to give me something else, I can also do that as well. No, not a
I
problem.
want to give you these two things like this voltage Salaya super and Heinkel super. This is 220 kV, this is 400 kV. So I will give you the. Do you want the Excel sheet or do you want to do it on Word? So if you want me to give the Excel sheet, I can give you. Simple, just
No,
like
no,
that you can do.
it's fine. I can watch the video and I can create the Excel sheet on my own and I can do that. It's not a problem. You explain it very well, so it's not a big deal. I may not
Anyway,
have the standard, but
okay.
I will watch this video. It will be saved in the recording. Is that right?
Yes, of course it will. And anyway, I will send you the Excel sheet as well. Just take that as reference and like take the formula from them, from the
Yes.
formula from the Excel sheet, and do it.
Yes. Yeah,
Yeah,
I will
that
do.
would be
No
great.
problem. Yeah,
Yeah.
yeah. I
So
will do it.
next class, we can discuss this both source modeling what you have done. This Salaya
Exactly.
Super and Nine College.
Salaya Super and Khalid Super. Yeah, one is the
The fourth
400.
one is the fourth one is same as the third one. So don't do that. Like it just same the repeated thing.
Yeah, so I need to verify basically 3943 and in 220 33 and 33 37.27. Right.
Yes, exactly. So
Yes, I will definitely do it, and it's very clear to me, and I don't think I will create any mistake. Hopefully.
if you have
Like,
any mistake, like please let us know it. We can discuss on next class and
oh yeah,
we
yeah.
will make.
Mistake are always good. That's how you learn. But no, what I'm trying to say is you basically taught me quite well, and I don't think there will be any mistake.
Yeah. So, so can you conclude today's session what we have done, because
Yes.
this is
So
what
the
we have planned for
so
today's session.
the takeaway for me is basically first thing is the very important thing is the RMS and the peak system in PSCAD. That's one of the key and very important thing where I was trying to bang my head and I was getting nowhere. And how I can verify the voltage and how I can use the RMS. That's one most of the basic thing I learned, like because I was creating the circuit without logic. And then another very good thing is like how to model a real source with a positive zero and a negative sequence component based on the client provided data and how to calculate these based on IEC 60909. I think that's what the standard was. Yeah. So yeah, I I learn a lot today, certainly a lot.
So fine. So yeah, tomorrow. So basically, you are going to see the source modeling. If you have done the source modeling, we can discuss that, and we have some. We can see the OHL modeling, like the transmission line modeling.
Yes.
So fine, Imanshu. Thank you, and we can meet it. We can meet you tomorrow.
Yeah, same time. Yeah, that would be great.
Yeah.
And thank you so much for your time. And please look for that PSCAD thing from Venkat.
Yes, of course. Yes, of course.
Yeah. If I get
Thank
it, is
you.
fine. But if not, then please for that.
Okay, Imanshu. Thank you.
Thank you. Have a nice evening. Bye.
Yeah, bye.